The crocodile paradox. When logic devours itself, picture this ancient scenario. A crocodile snatches a child from the riverbank and makes a deal with the distraught parent. "I'll return your child," the crocodile says, "but only if you can correctly predict what I'm going to do." The parent, desperate and clever, responds, "You will not return my child." Now we're trapped in a logical nightmare. If the parent is correct, then the crocodile must return the child according to their agreement. But if the crocodile returns the child, then the parent's prediction was wrong, which means the crocodile shouldn't return the child. Conversely, if the parent is wrong, the crocodile keeps the child, making the prediction true, which means the crocodile should return the child. This paradox reveals the dangerous territory where self-reference meets conditional logic. It's not just a clever word puzzle. It exposes fundamental problems in how we construct logical systems. The crocodile paradox shows us that certain statements can create logical loops that have no satisfactory resolution. Ancient philosophers used this to explore the limits of rational discourse, and modern logicians still grapple with similar self-referential problems in computer science and artificial intelligence. The paradox forces us to question whether all logical problems have solutions, or whether some questions are inherently unanswerable. 2. The liar paradox. The statement that breaks reality, "This statement is false." These 4 simple words have tormented philosophers, mathematicians, and logicians for over 2 millennia. At first glance, it seems like a harmless sentence, but when we examine it closely, it reveals a crack in the foundation of truth itself. If the statement is true, then it must be false, as it claims to be. But if it's false, then it's telling the truth about being false, which makes it true. We're caught in an infinite loop of contradiction, a logical perpetual motion machine that defies resolution. The ancient Greeks knew this paradox well. Epimenides the Cretan allegedly said, "All Cretans are liars," creating a similar self-referential trap. But the implications go far beyond ancient philosophy. In the 20th century, this paradox helped mathematicians like Kurt Gödel prove that no logical system can be both complete and consistent. It's a cornerstone of understanding the limits of formal systems, computation, and even artificial intelligence. The liar paradox isn't just an intellectual curiosity. It has a window into the deepest questions about truth, language, and reality. It shows us that our most basic concepts, like truth and falsehood, might be more fragile than we ever imagined. Every time we encounter it, we're forced to confront the possibility that some aspects of reality might be fundamentally paradoxical. 3. The barber paradox. Who shaves the shaver? In a small town, there lives a barber who shaves all and only those men who do not shave themselves. This seems like a perfectly reasonable arrangement until we ask the crucial question: who shaves the barber? If the barber shaves himself, then he belongs to the group of men who shave themselves, which means he shouldn't shave himself according to his own rule. But if he doesn't shave himself, then he belongs to the group of men who don't shave themselves, which means he should shave himself according to his profession. This delightful paradox, popularized by Bertrand Russell, is more than just a cute logical puzzle. It is actually a simplified version of Russell's famous paradox about the set of all sets that do and contend themselves. The barber paradox reveals the dangerous territory we enter when we create categories that reference themselves. The implications ripple through mathematics, computer science, and philosophy. It shows us that naive set theory leads to contradictions, forcing mathematicians to develop more sophisticated logical foundations. In computer science, it relates to problems of self-reference in programming languages. Philosophically, it challenges our understanding of classification and definition. The barber paradox teaches us that even simple, everyday concepts can hide profound logical difficulties. It's a reminder that the world of logic is full of surprises, and that clarity in definition doesn't always lead to clarity in application. 4. The omnipotence paradox. Can God create a rock too heavy for God to lift? This paradox strikes at the heart of one of humanity's most profound concepts: ultimate power. If a being is truly omnipotent, can they create a stone so heavy that even they cannot lift it? The question seems to trap omnipotence in a logical vice. If the omnipotent being can create such a stone, then there exists something they cannot do, which contradicts their omnipotence. If they cannot create such a stone, then there's something they cannot do, which also contradicts their omnipotence. Either way, omnipotence seems to be self-contradictory. This paradox has challenged theologians, philosophers, and logicians for centuries. Some argue that omnipotence doesn't mean the ability to do logically impossible things, just as God cannot create a square circle. Perhaps God cannot create a task that's impossible for God. Others suggest that the paradox reveals problems with our understanding of power and possibility rather than with omnipotence itself. The paradox extends beyond theology into questions about absolute concepts in general. Can there be a perfect defense against every possible attack? Can there be an irresistible force meeting an immovable object? These questions reveal the tension between absolute concepts and logical consistency. Modern approaches often focus on refining what we mean by omnipotence or examining the logical structure of the question itself. The paradox remains a powerful tool for exploring the limits of power, possibility, and logical consistency. 5. The unexpected hanging paradox. When prediction defeats itself. A judge sentences a prisoner to death, telling him, "You will be hanged at noon on one of the weekdays next week, but the hanging will be a surprise. You will not know which day it will be until the morning of the hanging." The prisoner thinks about this and concludes he cannot be hanged at all. His reasoning seems sound. If he's still alive on Friday morning, he'll know he's being hanged that day, so it won't be a surprise. Therefore, he can't be hanged on Friday. But if Friday is eliminated, then if he's still alive on Thursday morning, he'll know he's being hanged that day, so it won't be a surprise. By this logic, he eliminates every day of the week. Satisfied with his reasoning, the prisoner is genuinely surprised when the executioner arrives Wednesday morning. The hanging proceeds as scheduled, and it is indeed a surprise. This paradox exposes the complex relationship between knowledge, prediction, and surprise. The prisoner's logical reasoning seems flawless, yet it leads to a false conclusion. The paradox suggests that sometimes the very act of trying to predict or prevent something can create the conditions for it to occur unexpectedly. The unexpected hanging paradox has applications in game theory, where players' attempts to predict opponents' strategies can lead to similar logical loops. It also relates to problems in artificial intelligence about self-referential reasoning and prediction. The paradox shows us that logic and surprise can coexist in ways that challenge our understanding of both rational thought and the nature of knowledge itself. 6. Achilles and the tortoise. The fastest runner who cannot win in this famous paradox from Zeno of Elea. The swift-footed Achilles races against a tortoise. Being a good sport, Achilles gives the tortoise a head start. But Zeno argues that Achilles can never overtake the tortoise, no matter how fast he runs. Here's the reasoning. Before Achilles can pass the tortoise, he must first reach the point where the tortoise started. But by the time Achilles reaches that point, the tortoise has moved a little further ahead. Now Achilles must reach this new point. But again, by the time he gets there, the tortoise has moved a bit more. This process continues infinitely. Achilles must always reach where the tortoise was, never where it is. This paradox seems to prove that motion is impossible, or at least that faster objects cannot overtake slower ones. Yet we know from everyday experience that runners do overtake each other. The paradox creates a collision between logical reasoning and observable reality. The resolution involves understanding infinite series and limits. While Achilles must complete infinitely many tasks, the time required for each task decreases geometrically, and the total time converges to a finite value. Mathematically, we can show that Achilles will indeed overtake the tortoise. But the paradox remains philosophically profound. It reveals the counterintuitive nature of infinity and the mathematical concept of limits. It shows us that infinite processes can have finite outcomes, a concept that's crucial in calculus and mathematical analysis. A paradox also highlights the difference between mathematical idealization and physical reality. 7. The grandfather paradox. Breaking the chain of causality time. Travel stories often grapple with this mind-bending scenario. You travel back in time and prevent your grandfather from meeting your grandmother. Without their meeting, your parent is never born, which means you're never born, which means you can't travel back in time to prevent their meeting. But if you don't prevent their meeting, then you are born, and you can travel back to prevent it. This paradox strikes at the heart of causality, the fundamental relationship between cause and effect that seems to govern our universe. If effects can precede their causes through time travel, then the logical structure of reality appears to collapse. Various solutions have been proposed. The Novikov self-consistency principle suggests that the universe somehow prevents paradoxes from occurring. Perhaps your gun jams, or you trip and fall at the crucial moment. The many worlds interpretation proposes that changing the past creates a new timeline, leaving the original timeline intact. Some argue that the paradox proves time travel is impossible. The grandfather paradox isn't just science fiction speculation. It relates to deep questions in physics about the nature of time, causality, and the structure of spacetime. Einstein's relativity allows for closed time-like curves in certain exotic spacetime geometries, making the paradox a legitimate concern for theoretical physics. The paradox also illuminates philosophical questions about personal identity, free will, and the nature of possibility. It forces us to examine our assumptions about the fixed nature of the past and the open nature of the future. Even if time travel proves impossible, the grandfather paradox reveals important truths about the logical structure of temporal reality. 8. The Sorites paradox. When does a heap stop being a heap? Start with a heap of sand containing 100,000 grains. Remove one grain. Surely you still have a heap. Remove another grain. Still a heap. The paradox asks, at what point does the heap stop being a heap? If removing a single grain never transforms a heap into a non-heap, then even one grain should constitute a heap. But this seems absurd. This ancient paradox, attributed to Eubulides of Miletus, exposes the problem of vagueness in language and concepts. Most of our everyday categories, heap, bald, tall, red, have fuzzy boundaries. The paradox shows that Sorites' susceptible predicates resist precise definition. The implications extend far beyond sand heaps. When does a collection of cells become a person? When does a gradual change become a revolution? When does a company become a monopoly? These questions reveal that vagueness permeates our conceptual framework, affecting law, ethics, and science. Various solutions have been proposed. Some argue for precise cutoff points, accepting that the boundaries are arbitrary but necessary. Others embrace fuzzy logic, where statements can be partially true. Multi-valued logic systems allow for degrees of truth between completely true and completely false. The Sorites paradox challenges our binary thinking about categories. It suggests that the world might be inherently vague, not just our descriptions of it. This has profound implications for philosophy, artificial intelligence, and any field that requires precise categorization of continuous phenomena. The paradox also reveals the difference between practical and theoretical reasoning. In practice, we successfully navigate vague concepts every day. Theoretically, vagueness creates logical problems that resist easy solution. 9. Russell's paradox, the set that breaks mathematics. Bertrand Russell discovered a paradox that shook the foundations of mathematics. Consider the set of all sets that do not contain themselves. Does this set contain itself? If it does, then it doesn't belong to the set of sets that don't contain themselves. If it doesn't, then it belongs to the set of sets that don't contain themselves, which means it contains itself. This paradox emerged from Russell's work on set theory, which was supposed to provide a logical foundation for all of mathematics. Georg Cantor had developed naive set theory based on the principle that any well-defined property could determine a set. Russell showed that this principle leads to contradictions. The paradox isn't just a mathematical curiosity. It revealed fundamental problems with the logical foundations of mathematics. It showed that naive set theory was inconsistent, forcing mathematicians to develop more sophisticated axiomatic systems like Zermelo-Fraenkel set theory. Russell's paradox relates to broader questions about self-reference and the limits of formal systems. It's connected to the liar paradox and similar self-referential problems that appear throughout logic and mathematics. The paradox helped inspire Kurt Gödel's incompleteness theorems, which showed that any sufficiently powerful mathematical system must be either incomplete or inconsistent. The implications extend beyond mathematics into computer science, philosophy, and cognitive science. The paradox reveals the dangers of unrestricted abstraction and the importance of carefully constructed logical systems. It shows that even our most basic mathematical concepts require careful definition, and that the foundations of knowledge are more fragile than we might expect. 10. Zeno's arrow paradox. The motion that cannot be at any instant in time. A flying arrow occupies a space exactly equal to its own dimensions. Within this space, the arrow cannot move. There's no room for motion. But if the arrow cannot move at any instant, how can it move through time? Motion seems to require that the arrow be in different places at different times, yet at each specific time, it's motionless. This paradox, another of Zeno's famous arguments against motion, challenges our intuitive understanding of movement and change. It suggests that motion might be an illusion created by our limited perception of reality's true nature. The paradox exposes the relationship between time, space, and motion. If time consists of indivisible instants, then motion becomes impossible. But if time is infinitely divisible, then motion requires completing infinitely many tasks, which also seems impossible. Modern physics and mathematics provide frameworks for understanding motion that resolve Zeno's paradox. Calculus allows us to define instantaneous velocity as the limit of average velocities over increasingly small time intervals. We can describe motion mathematically without requiring the arrow to actually move during an instant. But the paradox remains philosophically significant. It reveals the difference between mathematical descriptions of motion and the physical reality of motion. It also highlights the relationship between continuous and discrete models of space and time. The arrow paradox connects to broader questions about the nature of time, change, and continuity. It suggests that our everyday experience of motion might be fundamentally different from the underlying reality. Even with mathematical solutions, the paradox continues to challenge our understanding of the relationship between mathematics and physical reality. 11. The ship of Theseus. When everything changes, what remains? The legendary ship of Theseus returns to Athens after many adventures, but during its long journey, the crew gradually replaced every plank, rope, and sail due to wear and damage. By the time it reaches port, not a single original piece remains. The question that has puzzled philosophers for millennia: is this still the same ship? This paradox becomes even more complex when we consider that the discarded original pieces were collected and reassembled into a ship. Now we have two ships, one with the original materials and one with the original form and function. Which one is the real ship of Theseus? The paradox strikes at the heart of identity and persistence through change. In our daily lives, we assume that objects maintain their identity despite gradual changes. Your body replaces most of its cells every 7 years, yet you remain you, A river's water constantly flows, yet we call it the same river. The ship paradox forces us to examine what we mean by sameness and identity. Different philosophical traditions offer varying solutions. Some argue that identity lies in material continuity. The ship with original planks is the true ship. Others emphasize functional continuity. The ship that maintained its purpose and form is authentic. Still others suggest that identity is conventional, determined by how we choose to categorize and name things. The paradox has profound implications for personal identity, consciousness, and the nature of objects. It relates to questions about artificial intelligence, consciousness uploading, and the persistence of identity through radical change. The ship of Theseus reminds us that identity might be more fluid and arbitrary than we typically assume. 12. The brain in a vat. Are you living in a false reality? Imagine that you are actually a disembodied brain floating in a vat of nutrients, with electrodes stimulating your neurons to create the illusion of experiencing the external world. Everything you perceive, your body, your environment, other people, is just an elaborate simulation fed directly into your brain. How could you possibly know whether this is true or false? This modern version of ancient skeptical scenarios challenges our most basic assumptions about knowledge and reality. If all our evidence about the external world comes through our senses, and if our senses could be systematically deceived, then we seem to have no way of knowing whether our beliefs about reality are true. The paradox reveals the problem of external world skepticism. We believe we can trust our senses to tell us about reality, but our senses only provide us with experiences, not direct access to the world itself. The brain in a vat scenario suggests that identical experiences could be produced by either a real world or a perfect simulation. Philosophers have proposed various responses. Some argue that the scenario is meaningless because words like brain and vat derive their meaning from our interactions with the external world. Others suggest that the scenario is possible, but that we should trust our senses in the absence of evidence for deception. Still others embrace the uncertainty and argue that knowledge doesn't require certainty. The paradox has gained new relevance in the age of virtual reality and artificial intelligence. It relates to questions about consciousness, reality, and the nature of experience. The brain in a vat scenario forces us to examine the relationship between experience and reality, and to consider whether there might be aspects of existence that are forever beyond our knowledge. 13. Mary's room. The knowledge that cannot be taught. Mary is a brilliant color scientist who has spent her entire life in a black and white room, learning about color through black and white monitors. She knows everything physical about color: wavelengths, how the eye processes different frequencies, how the brain responds to color stimuli. But she has never actually seen color. The question: what happens when Mary first sees a red apple? This thought experiment, proposed by philosopher Frank Jackson, probes the relationship between physical knowledge and conscious experience. If Mary learns something new when she sees red for the first time, then there seems to be knowledge that cannot be captured by physical descriptions. This suggests that consciousness involves non-physical properties. The paradox highlights the hard problem of consciousness, explaining how subjective experiences arise from physical processes. Mary's situation seems to show that there are facts about consciousness that cannot be deduced from physical facts. Different philosophical positions offer varying interpretations. Physicalists argue that Mary doesn't actually learn new facts, but rather acquires new abilities or ways of accessing the same information. Dualists contend that Mary discovers genuinely new facts about the world, suggesting that consciousness involves non-physical properties. The thought experiment has implications for artificial intelligence, neuroscience, and philosophy of mind. It raises questions about whether machines could ever truly understand consciousness, whether neuroscience can fully explain subjective experience, and whether conscious experiences have properties that transcend physical description. Mary's Room forces us to confront the mystery of consciousness and the limits of objective knowledge. It suggests that there might be aspects of reality that can only be known through direct experience, never through abstract understanding. 14. The inverted spectrum. When my red is your blue. Consider this unsettling possibility. What if the color you see when looking at a ripe strawberry is the same color I see when looking at a clear sky? We both call strawberries red and the sky blue, but our internal, subjective experiences are completely inverted. Since we've both learned to associate the same words with the same objects, this difference would be undetectable. This thought experiment challenges our assumptions about shared experience and the privacy of consciousness. We typically assume that when two people look at the same red object, they have similar visual experiences. But the inverted spectrum suggests that our subjective experiences might be radically different, while remaining functionally identical. The paradox reveals the problem of other minds and the privacy of subjective experience. We have direct access only to our own consciousness, never to others. This means that differences in subjective experience might be undetectable if they don't affect behavior or function. The inverted spectrum relates to broader questions about the nature of consciousness and the relationship between objective and subjective reality. It suggests that there might be aspects of experience that are inherently private and incommunicable. Even if we develop perfect brain scanning technology, we might never be able to directly compare subjective experiences. Some philosophers argue that the inverted spectrum scenario is meaningless because color experiences are constituted by their functional roles. Others maintain that it reveals important truths about the nature of consciousness and the limits of scientific knowledge about subjective experience. The paradox has implications for understanding empathy, communication, and the possibility of artificial consciousness. It raises questions about whether we can ever truly know if others experience the world as we do, and whether machines could have subjective experiences that differ from ours in undetectable ways. 15. The persistence of identity. Are you the same person you were yesterday? Every cell in your body is replaced over time, some within days, others over years. Your thoughts, memories, and personality continuously evolve. The atoms that compose you today are different from those that composed you a decade ago. In what sense, if any, are you the same person you were in childhood? This paradox extends beyond physical change to psychological transformation. Your beliefs, values, and personality have undoubtedly changed over time. You've forgotten countless experiences and learned new things. The person you are today might disagree with decisions made by your past self. What makes you you across time? Various theories attempt to solve this puzzle. Physical continuity theories argue that identity depends on bodily continuity despite cellular replacement. Psychological continuity theories focus on memory, personality, and mental patterns. Soul theories posit an immaterial essence that persists through change. The paradox has practical implications for ethics, law, and personal responsibility. If you're not the same person who committed a crime years ago, should you be punished? If your personality changes dramatically due to brain injury, are you still the same person? These questions affect how we think about moral responsibility and personal relationships. The persistence of identity paradox also relates to questions about consciousness, free will, and the nature of the self. It suggests that identity might be more fluid and constructed than we typically assume. Rather than being fixed entities, we might be continuously changing processes that maintain certain patterns over time. Modern neuroscience and psychology provide new perspectives on identity, showing how brain changes affect personality and memory. The paradox remains relevant for understanding consciousness, aging, and the relationship between mind and body. 16. The swampman. When nature creates a perfect copy lightning, strikes a swamp just as you're walking through it, instantly vaporizing your body. By an incredible coincidence, the same lightning strike rearranges the carbon atoms in the swamp to create a molecule-for-molecule duplicate of your body, complete with all your memories, personality, and physical characteristics. This swampman walks out of the swamp, returns to your home, and continues your life. Is the swampman you? This thought experiment, proposed by philosopher Donald Davidson, probes the relationship between identity and origin. The swampman is physically and mentally identical to you, but lacks your causal history. It has never actually experienced the events it remembers or learned the skills it possesses. The paradox reveals tensions between different theories of identity and meaning. If identity depends on physical and psychological continuity, then the swampman seems to be you. But if identity requires proper causal history, then the swampman is merely a copy, regardless of how perfect. The scenario also raises questions about the nature of memory, knowledge, and meaning. Can the swampman truly remember events it never experienced? Does it really know things it never learned? These questions challenge our understanding of mental states and their relationship to past experiences. The swampman paradox has implications for consciousness, artificial intelligence, and the nature of persons. It relates to questions about whether perfect copies could have consciousness, whether teleportation would preserve identity, and whether meaning depends on causal history. Different philosophical traditions offer varying responses. Some argue that the swampman is identical to you in all meaningful ways. Others maintain that proper causal history is essential for identity and meaning. The paradox forces us to examine what we consider essential to personal identity and conscious experience. 17. The teleporter paradox. Death and rebirth every morning. You step into a teleporter that scans your body down to the quantum level, stores the information, and transmits it to Mars, where another machine reconstructs you exactly. But the process requires destroying your original body to avoid having two copies. The question that keeps you awake at night: is the person who steps out on Mars you, or merely a copy with your memories who thinks they're you? This scenario, popular in science fiction, forces us to confront deep questions about identity, consciousness, and death. If the reconstructed person has all your memories, personality, and physical characteristics, in what sense might they not be you? Yet if you're destroyed in the process, it seems like you've died, regardless of what emerges on Mars. The paradox becomes more complex when we consider variations. What if the original body isn't destroyed? Then you'd have two people with equal claim to being you. What if the process takes time, leaving you unconscious between destruction and reconstruction? Does the gap in consciousness affect your identity? The teleporter paradox reveals the assumption that consciousness is continuous and unified. We typically think of ourselves as persisting through time, but the teleporter suggests that consciousness might be more fragmented than we realize. We already experience gaps in consciousness during sleep and anesthesia without questioning our identity. Different philosophical positions offer varying interpretations. Physicalists might argue that exact physical reconstruction preserves identity. Dualists might question whether consciousness can be captured and transmitted. Buddhist philosophy might suggest that the self is already an illusion, making the paradox meaningless. The paradox has practical implications for emerging technologies, like consciousness uploading and advanced life support. It forces us to examine what we value about continued existence and what we fear about death. 18. Moravec's paradox. Why computers excel at chess, but struggle with childhood tasks. Hans Moravec observed a puzzling phenomenon. Computers can defeat world chess champions and solve complex mathematical problems, yet they struggle with tasks that any 4-year-old can accomplish effortlessly, like recognizing faces, understanding speech, or navigating cluttered spaces. Why is artificial intelligence so good at what humans find difficult, yet so poor at what humans find easy? This paradox reveals fundamental differences between human and artificial intelligence. Tasks that feel effortless to humans often require sophisticated unconscious processing that evolved over millions of years. Recognizing a face involves complex pattern recognition that our brains perform automatically, while playing chess requires conscious logical reasoning that can be programmed systematically. The paradox suggests that human intelligence is not simply a matter of processing power or logical reasoning. Much of our intelligence operates below the threshold of consciousness, handling sensory processing, motor control, and social interaction through specialized neural circuits refined by evolution. Moravec's paradox has profound implications for artificial intelligence research. It suggests that creating human-like AI might require not just better algorithms, but fundamentally different approaches that capture the unconscious processing that makes human intelligence possible. The paradox also reveals assumptions about intelligence and difficulty. We tend to equate intelligence with abstract reasoning and complex problem-solving, but Moravec's paradox suggests that the most impressive aspects of intelligence might be the ones we take for granted. Recent advances in deep learning and neural networks have begun to address some aspects of Moravec's paradox, enabling computers to recognize images and understand speech more effectively. But the paradox remains relevant for understanding the nature of intelligence and the challenges of creating truly artificial minds. 19. The qualia problem, describing the indescribable. How do you describe the redness of red to someone who has never seen color? How do you explain the taste of chocolate or the sound of music to someone who has never experienced these sensations? This challenge reveals the problem of qualia, the subjective, conscious experiences that seem to resist objective description. Qualia are the what-it's-like aspects of conscious experience. There's something it's like to see red, taste chocolate, or feel pain that seems to go beyond any physical description of these experiences. This subjective dimension of consciousness appears to be irreducible to objective third-person descriptions. The qualia problem challenges physicalist theories of mind that attempt to explain consciousness in terms of brain states and neural processes. If conscious experiences have irreducible subjective properties, then consciousness might involve more than just physical processes. The problem has implications for artificial intelligence, neuroscience, and philosophy of mind. Can machines have subjective experiences? Can neuroscience fully explain consciousness? Are there aspects of reality that are inherently subjective and cannot be captured by objective science? Different philosophical positions offer varying approaches to the qualia problem. Some argue that qualia are real and irreducible features of consciousness. Others maintain that qualia are illusions that can be explained by physical processes. Still others suggest that the problem reveals limitations in our conceptual frameworks rather than genuine mysteries about consciousness. The qualia problem also relates to questions about empathy, communication, and the possibility of shared experience. If qualia are private and incommunicable, then we might never truly understand others' experiences. This raises questions about the nature of understanding and the limits of knowledge. 20. The philosophical zombie. Consciousness without experience. Imagine a being that is physically identical to you in every way. Every atom in the same place, every neural connection identical, every behavior pattern matching yours perfectly. This being acts conscious, claims to have experiences, and passes every test for consciousness. But it has no inner subjective experience, no qualia, no what it's like to be that being. This is a philosophical zombie. The zombie argument, developed by philosopher David Chalmers, challenges physicalist theories of consciousness. If zombies are conceivable, then consciousness might involve more than just physical processes. The argument suggests that there's an explanatory gap between physical processes and subjective experience. The zombie scenario seems to show that consciousness has irreducible subjective properties. If a being could be physically identical to you, but lack consciousness, then consciousness cannot be fully explained by physical properties alone. This suggests that consciousness might involve non-physical properties, or that physicalism is false. Critics argue that zombies are not actually conceivable, or that conceivability doesn't entail possibility. They maintain that consciousness is necessarily connected to physical processes, and that beings identical to us must be conscious. The debate reveals deep disagreements about the nature of consciousness and its relationship to physical reality. The zombie argument has implications for artificial intelligence, cognitive science, and ethics. If consciousness requires more than physical processes, then current AI systems might be zombies rather than truly conscious beings. This raises questions about machine consciousness and the moral status of artificial beings. The philosophical zombie paradox forces us to examine our assumptions about consciousness, physicalism, and the relationship between mind and matter. It suggests that consciousness might be more mysterious and fundamental than we typically assume, resistant to purely physical explanation. 21. The bootstrap paradox. Information without origin. A time traveler goes back to meet Shakespeare and discovers that the great playwright is actually an illiterate tavern keeper who has never written a word. Disappointed, the time traveler recites Hamlet from memory, inspiring the tavern keeper to write it down and claim it as his own work. But where did Hamlet actually come from? The time traveler learned it from Shakespeare, but Shakespeare learned it from the time traveler. This paradox reveals the strange logical loops that closed time-like curves can create. Information, objects, or even people can exist in causal loops where they are their own cause. The bootstrap paradox suggests that some things might exist without any ultimate origin or explanation. The paradox becomes even more puzzling when we consider that the information in the loop might be degraded or enhanced with each iteration. Would Hamlet remain identical through multiple loops, or would it gradually change? Could information actually improve through bootstrap processes? The bootstrap paradox has implications for understanding causation, explanation, and the nature of information. It suggests that not everything that exists needs to have an ultimate origin or first cause. Some things might exist in self-sustaining causal loops that have no beginning or end. The paradox also relates to questions about free will and determinism. If events are their own causes, then the usual distinction between cause and effect breaks down. This might suggest that reality is more complex and interconnected than linear causation would imply. Modern physics allows for closed time-like curves in certain exotic space-time geometries, making the bootstrap paradox a legitimate concern for theoretical physics. The paradox forces us to examine our assumptions about causation, time, and the structure of reality. 22. The twin paradox. When time becomes relative, twin siblings Alice and Bob are both 20 years old. Alice travels to a distant star at 99% the speed of light, while Bob remains on Earth. When Alice returns, she has aged only 2 years and is now 22, while Bob has aged 20 years and is now 40. From Alice's perspective, her journey took 2 years, but from Bob's perspective, it took 20 years. How can this be? This paradox emerges from Einstein's special theory of relativity, which reveals that time is not absolute, but depends on relative motion. Time literally slows down for objects moving at high speeds relative to other objects. This time dilation effect becomes dramatic at speeds approaching the speed of light. The paradox seems to create a contradiction. If motion is relative, shouldn't Bob age more slowly from Alice's perspective? The resolution lies in recognizing that the situation is not perfectly symmetric. Alice must accelerate to turn around and return to Earth, breaking the symmetry and making her the one who ages more slowly. The twin paradox reveals the counterintuitive nature of spacetime and the relativity of simultaneity. Events that are simultaneous in one reference frame are not simultaneous in another. This means that the question, "What time is it now on Earth?" has no absolute answer for Alice during her journey. The paradox has been experimentally verified using atomic clocks on airplanes and high-speed particles in accelerators. It's not just a theoretical curiosity, but a real effect that must be accounted for in GPS, satellites, and particle physics experiments. The twin paradox challenges our intuitive understanding of time and forces us to reconceptualize the nature of temporal reality. It suggests that time is not a universal constant, but a flexible dimension that responds to motion and gravity. 23. The predestination paradox. Causing what you tried to prevent. You travel back in time after learning that a specific disaster occurred on a particular date. Determined to prevent this catastrophe, you arrive in the past and take actions to stop it. However, your very presence and actions turn out to be the cause of the disaster you are trying to prevent. Your attempt to change history becomes the reason history happened as it did. This paradox reveals the potential for self-fulfilling prophecies in time travel scenarios. It suggests that the future might be fixed not because events are predetermined, but because attempts to change them actually cause them. The predestination paradox shows how causal loops can make the future seem inevitable while maintaining the appearance of free will. The paradox has ancient roots in mythology and literature, from Oedipus's attempt to avoid his prophesied fate to modern science fiction stories. It explores the tension between determinism and free will, suggesting that knowledge of the future might paradoxically ensure that future comes to pass. The predestination paradox raises profound questions about the nature of causation and responsibility. If your actions in the past caused the disaster you are trying to prevent, are you responsible for it? The paradox suggests that moral responsibility becomes complex when causal chains form loops. The paradox also relates to questions about the nature of time and possibility. If the future is fixed through causal loops, then what we experience as free choice might be an illusion. Alternatively, the paradox might suggest that there are multiple possible timelines and that our choices determine which one we experience. 24. Novikov's self-consistency principle. The universe that prevents paradoxes. Physicist Igor Novikov proposed that the universe operates according to a self-consistency principle that prevents paradoxes from occurring. According to this principle, any events that occur in spacetime must be self-consistent. The universe somehow conspires to prevent actions that would create logical contradictions. Under this principle, if you try to go back in time to kill your grandfather, something will always prevent you from succeeding. Your gun might jam, you might trip at the crucial moment, or you might discover that the person you thought was your grandfather actually wasn't. The universe maintains consistency by making paradox-creating actions impossible. This principle suggests that space-time has a kind of logical structure that prevents contradictions. It's not that time travel is impossible, but that time travel can only occur in ways that maintain consistency with what has already happened. The future and past form a self-consistent whole. Novikov's principle has implications for free will and determinism. If the universe prevents certain actions to maintain consistency, then our choices might be more constrained than we realize. The principle suggests that what we experience as free will operate within the bounds of logical consistency. The principle also relates to quantum mechanics and the nature of possibility. Some interpretations suggest that quantum effects might provide the mechanism by which the universe maintains consistency, with quantum uncertainties conspiring to prevent paradoxes. 25. The causal loop. Effect becoming its own cause. A causal loop occurs when an event is among the causes of itself, creating a chain of causation that has no beginning or end. In time travel scenarios, this might involve an object or piece of information that exists only within the loop, with no external origin. The loop is self-sustaining and self-explaining. Consider a scenario where you receive a note from your future self with instructions that lead you to travel back in time and give your past self the same note. The note exists only within the causal loop. It has no author and no origin. It simply exists as a feature of the self-consistent spacetime structure. Causal loops challenge our understanding of causation and explanation. We typically expect events to have causes that precede them in time, but causal loops show that causation can be circular. This suggests that not all events need ultimate explanations or first causes. The existence of causal loops might be related to fundamental features of spacetime geometry. In general relativity, certain exotic spacetime configurations allow for closed time-like curves that make causal loops possible. While such configurations require exotic matter with negative energy density, they are not forbidden by known physical laws. Causal loops also raise questions about information and entropy. If information can exist in causal loops without external input, this might violate thermodynamic principles about information conservation. The resolution of this problem might require new understanding of the relationship between information, causation, and the structure of spacetime. 26. The many worlds paradox. Every possibility happens somewhere. According to the many worlds interpretation of quantum mechanics, every time a quantum event occurs, the universe splits into multiple branches representing all possible outcomes. This means that every possible version of history actually happens somewhere in the infinite multiverse of parallel worlds. This interpretation solves certain paradoxes by making all possibilities real. The grandfather paradox disappears because killing your grandfather simply creates a new branch of reality where you were never born, while the original branch continues unchanged. Time travel doesn't change history. It creates new histories. But the many worlds interpretation creates new paradoxes. If every possible version of you exists across the multiverse, which one is the real you? If all possible outcomes occur, do your choices matter? If there are versions of you that make every possible decision, what does moral responsibility mean? The many worlds interpretation also raises questions about probability and prediction. If all outcomes occur, why do we observe some more frequently than others? The interpretation requires a new understanding of probability as a measure of the proportion of branches with particular outcomes. The paradox extends to questions about consciousness and identity. Are you connected to your alternate selves in other branches? Do you experience all possible lives simultaneously, or only one? These questions challenge our understanding of personal identity and conscious experience. 27. The block universe, past, present, and future. All exist now. According to Einstein's relativity, all events in spacetime exist equally. The past, present, and future are all real and exist simultaneously in what physicists call the block universe, or eternalism. From this perspective, time is like space. All moments exist, but we only experience them sequentially. This view creates profound paradoxes for our understanding of time and change. If all moments exist equally, then what makes the present special? Why do we experience time as flowing from past to future if all times exist simultaneously? The block universe suggests that our experience of temporal flow might be an illusion. The paradox becomes more acute when we consider free will and possibility. If the future already exists, are our choices predetermined? Can we change what will happen if it already exists in the block universe? The eternalist view seems to eliminate genuine possibility and make free will illusory. Different philosophical positions attempt to resolve these paradoxes. Some argue that while all times exist, there are objective facts about which events are past, present, and future. Others maintain that temporal concepts like now are relative to observers and have no absolute meaning. The block universe also raises questions about death and personal identity. If all moments of your life exist eternally in the block universe, are you immortal in some sense? Does death have meaning if your entire life exists timelessly? 28. The chronology protection conjecture. Why we don't see. Time traveler Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics conspire to prevent the formation of closed time-like curves that would allow travel to the past. According to this conjecture, whenever space-time begins to develop the geometry necessary for time travel, quantum effects destroy the time machine before it can be activated. This conjecture explains why we don't encounter time travelers from the future. If time machines are possible in principle, but prevented by physical laws, then they will never actually be built. The universe protects its own consistency by preventing paradox-creating devices from functioning. The conjecture suggests that there might be fundamental limits to what is physically possible, even if something is allowed by the basic equations of physics. Quantum effects, vacuum fluctuations, or other mechanisms might enforce consistency at a deeper level than classical general relativity. The chronology protection conjecture raises questions about the relationship between physical possibility and logical consistency. It suggests that the universe might have built-in mechanisms for avoiding logical contradictions, even if this requires preventing certain physical processes. The conjecture also relates to the anthropic principle and the fine-tuning of physical constants. Perhaps the laws of physics are structured to prevent paradoxes, because universes that allow paradoxes are logically unstable and cannot exist consistently. 29. The black hole information paradox. Where does information go? According to quantum mechanics, information cannot be destroyed. The total amount of information in the universe is conserved. But according to general relativity, information that falls into a black hole is lost forever when the black hole evaporates through Hawking radiation. This creates a fundamental conflict between two of our most successful physical theories. The paradox emerges because Hawking radiation appears to be purely thermal, carrying no information about what fell into the black hole. If black holes eventually evaporate completely, then the information that fell into them seems to disappear from the universe, violating quantum mechanical principles. Various solutions have been proposed. Some suggest that information is encoded in the Hawking radiation in subtle ways that preserve conservation laws. Others propose that information is stored at the black hole, S-event horizon, or that black holes do completely evaporate. The information paradox has deep implications for our understanding of spacetime, gravity, and quantum mechanics. It suggests that one of our fundamental theories is incomplete or incorrect. The resolution might require a new theory of quantum gravity that unifies relativity and quantum mechanics. The paradox also raises questions about the nature of information itself. What exactly is information in physics? How is it related to entropy and the structure of spacetime? These questions are central to understanding the deepest levels of physical reality. 30. The problem of time's direction. Why does time have an arrow? The fundamental laws of physics are largely time-symmetric. They work the same way forward and backward in time. Yet we experience time as having a definite direction, flowing from past to future. We remember the past, but not the future. We see cups break, but not spontaneously reassemble, and entropy increases over time. Why does time have an arrow if the basic laws are symmetric? This paradox reveals a deep mystery about the nature of time and causation. The apparent asymmetry of time seems to emerge from symmetric laws, suggesting that time as arrow might be a statistical or thermodynamic phenomenon rather than a fundamental feature of physics. The second law of thermodynamics provides one explanation. Entropy tends to increase over time, giving time a preferred direction. But this raises new questions. Why was the entropy of the early universe so low? Why do we define the direction of increasing entropy as forward in time? The arrow of time might be related to the expansion of the universe, the nature of causation, or quantum mechanical processes. Some theories suggest that time as arrow emerges from the way information propagates through spacetime, or from the structure of quantum entanglement. The problem has implications for cosmology, consciousness, and the nature of physical law. If time's arrow is not fundamental, then our experience of temporal flow might be an emergent property of complex systems rather than a basic feature of reality. 31. The Monty Hall problem. Why switching wins? You're on a game show facing 3 doors. Behind one is a car. Behind the other 2 are goats. You pick door number 1. The host, who knows what's behind each door, opens door number 3 to reveal a goat. Now you can switch to door number 2 or stick with door number 1. Surprisingly, switching gives you a 2/3 chance of winning the car, while sticking gives you only 1/3. This counterintuitive result has baffled millions of people, including many mathematicians who initially got it wrong. The key insight is that the host's action of opening a door provides information that changes the probabilities. When you first chose, door number 1 had a 1/3 chance of having the car, leaving a 2/3 chance that the car was behind one of the other doors. When the host opens door number 3 and shows a goat, that 2/3 probability doesn't disappear. It gets concentrated entirely on door number 2. The host's knowledge and deliberate choice to reveal a goat transfers probability from the open door to the remaining unopened door. The paradox reveals how our intuitions about probability can mislead us. Many people think that with 2 doors remaining, each should have a 50% chance, but this ignores the information provided by the host's action. The problem demonstrates the importance of conditional probability and how new information can change probability assignments. The Monty Hall problem has applications in decision theory, game theory, and statistics. It shows how strategic behavior and asymmetric information can affect optimal decision-making. The paradox also reveals the difference between random selection and informed choice in probability problems. 32. Bertrand's paradox, the problem of random chords. Here is a seemingly simple geometric problem. What is the probability that a randomly chosen chord of a circle is longer than the side of an inscribed equilateral triangle? The paradox is that different reasonable methods of choosing the chord randomly give different answers. 1/2, 1/3, or 1/4. Method 1. Choose 2 random points on the circle circumference and connect them. Each method seems like a reasonable interpretation of random chord, yet they yield different results. The paradox reveals that the concept of random is not as straightforward as it appears. Randomness must be defined precisely with respect to a specific probability distribution. Bertrand's paradox highlights the importance of being explicit about probability models. It shows that seemingly equivalent descriptions of random processes can lead to different probability distributions and different answers to the same question. The paradox has implications for statistical inference, mathematical modeling, and the interpretation of probability. It suggests that probabilistic statements must always be understood relative to specific assumptions about the underlying random process. 33. Simpson's paradox. When trends reverse, a treatment appears successful in each of 2 hospitals individually, but when the data from both hospitals is combined, the treatment appears harmful. This paradox occurs when a trend that appears in separate groups disappears or reverses when the groups are combined. For example, imagine Hospital A treats 10 patients while Hospital B treats 100 patients. A new treatment is used on some patients. 2 out of 3 patients at Hospital A recover, and 20 out of 40 patients at Hospital B recover. The treatment appears to work better than the baseline in both hospitals. But overall, the treatment succeeds in 22 out of 43 cases, while the control group succeeds in 78 out of 67 cases. The treatment appears to be harmful when the data is combined, despite appearing beneficial at each hospital individually. Simpson's paradox occurs because the groups being compared have different characteristics that affect the outcome. In medical studies, it might be patient severity. In educational studies, it might be student background. A paradox shows that correlation and causation can appear to reverse depending on which variables are considered. The paradox has profound implications for data analysis, causal inference, and decision-making. It shows that statistical conclusions can depend crucially on how data is aggregated and which variables are controlled for. The paradox reveals the importance of understanding confounding variables in statistical analysis. 34. The birthday paradox. Surprising coincidences. In a group of just 23 people, there's a greater than 50% chance that 2 people share the same birthday. With 70 people, the probability exceeds 99.9%. This seems impossible because there are 365 possible birthdays, so we might expect to need hundreds of people before coincidences become likely. The paradox arises from our tendency to think about the probability that a specific person shares your birthday, rather than the probability that any 2 people share any birthday. With 23 people, there are 253 possible pairs, and each pair has a 1/365th chance of sharing a birthday. The calculation involves finding the probability that no 2 people share a birthday, then subtracting from 1. For 23 people, this probability is approximately 49.3%, making the probability of at least one match about 50.7%. The birthday paradox illustrates how our intuitions about probability often fail us. We tend to underestimate the likelihood of coincidences and overestimate the number of trials needed for unlikely events to occur. The paradox shows the power of combinatorial analysis in probability theory. The principle behind the birthday paradox applies to many real-world situations. Hash collisions in computer science, genetic diversity in populations, and cryptographic security. Understanding the paradox is crucial for designing systems that must handle random events and potential conflicts. 35. The gambler's fallacy. When past results don't matter, after a coin has landed heads 5 times in a row, many people believe that tails is due, and more likely on the next flip. This belief, known as the gambler's fallacy, assumes that past results influence future probabilities in independent random events. In reality, each coin flip is independent of previous flips. The coin has no memory of past results, and the probability of heads or tails remains 50% on every flip, regardless of what happened before. The sequence HHHHH is exactly as likely as HTHTTH or any other specific sequence of 6 flips. The fallacy arises from our tendency to see patterns and expect balance in small samples. We intuitively expect random sequences to look random, meaning they should have roughly equal numbers of heads and tails without long runs of the same outcome. But truly random sequences often contain streaks that appear non-random. The gambler's fallacy has serious consequences in gambling, investing, and decision-making. It leads people to make irrational bets based on past results and to misinterpret random fluctuations as meaningful patterns. The fallacy shows how our pattern-seeking minds can lead us astray in probabilistic reasoning. Understanding the gambler's fallacy is crucial for properly interpreting statistical data and making rational decisions under uncertainty. It highlights the difference between independence and dependence in probability theory and the importance of understanding the true nature of random processes. 36. The 2 envelopes problem. The strategy that always wins. You're given 2 envelopes, one containing twice as much money as the other. You pick one envelope and find it contains $100. Should you switch to the other envelope? A seemingly logical argument suggests you should always switch, no matter what amount you find. The argument: if your envelope contains $100, the other envelope contains either $50 or $200, each with equal probability. The expected value of switching is $50 plus. $200 equals $125, which is greater than the $100 you currently have. Therefore, you should switch. But this logic seems to apply regardless of the amount in your envelope. If you found $1,000, the other envelope would contain $500 or $2,000, giving an expected value of $1,250. This suggests you should always switch, which seems paradoxical. The paradox reveals subtle issues in probability theory and decision theory. The problem is that the equal probability assumption may not be valid when considering all possible amounts. The resolution depends on the prior probability distribution, over possible amounts. If amounts are bounded or follow specific probability distributions, the paradox can be resolved. But if all positive amounts are equally likely, the paradox persists. The problem illustrates the importance of carefully specifying probability models and the dangers of informal probabilistic reasoning. 37. The Sleeping Beauty Problem, Probability and Perspective. Sleeping Beauty participates in an experiment. On Sunday, a fair coin is flipped. If heads, she's awakened once on Monday, and the experiment ends. If tails, she's awakened on Monday, given a memory-erasing drug, then awakened again on Tuesday. Each time she awakens, she's asked, "What's the probability the coin landed heads?" This problem has divided philosophers and probability theorists into two camps. The Haffer position emphasizes that the coin flip itself is unaffected by the experimental procedure. From a frequentist perspective, heads occurs in half of all experiments, so the probability should remain 1/2. The third position focuses on the conditional probability given that she's been awakened. Since awakening on Tuesday can only occur if the coin landed tails, and she can't distinguish Monday from Tuesday, she should update her probability based on this information. The problem reveals deep questions about the nature of probability, reference classes, and perspective in probability theory. It highlights the difference between objective probability and subjective probability. The Sleeping Beauty problem has implications for anthropic reasoning, quantum mechanics, and decision theory. It shows how the same objective situation can lead to different rational probability assignments depending on one's perspective and the reference class considered. 38. The Doomsday Argument. A statistical prediction of humanity's end. Consider all humans who will ever live, numbered in order of birth. You are one of these humans. The Doomsday Argument claims that you are likely to be roughly in the middle of this sequence, which means humanity probably won't last much longer than it has already existed. If humanity survives for millions more years with trillions of future people, then you would be among the earliest humans, a very improbable position. It's more likely that you're in a typical position among all humans, suggesting that the total number of humans won't be vastly larger than the current population. The argument applies the principle of mediocrity, or Copernican principle, the idea that we should unassume we occupy a special or privileged position. Just as we're not at the center of the universe, we probably aren't among the first tiny fraction of all humans who will ever live. Critics argue that the argument involves reference class problems. Which group of observers should we consider ourselves part of? They also question whether birth order provides relevant information about survival prospects, and whether the mediocrity principle applies to temporal position. The Doomsday Argument has been extended to other contexts, including the survival of species, civilizations, and even the universe itself. It raises profound questions about statistical reasoning, anthropic principles, and the appropriate reference classes for probabilistic inference. 39. The Anthropic Principle. Why the universe seems fine-tuned. The fundamental constants of physics appear to be fine-tuned for the existence of life. If the strong nuclear force were slightly different, stars couldn't form. If the electromagnetic force were different, atoms couldn't exist. The probability that all these constants would randomly fall within the narrow ranges necessary for life seems astronomically small. The anthropic principle provides a potential explanation. We observe a life-compatible universe, precisely because we exist to observe it. Universes without the right constants wouldn't have observers to notice their incompatibility with life. We shouldn't be surprised to find ourselves in a universe capable of supporting life, even if such universes are rare. The weak anthropic principle simply notes that observations must be compatible with the existence of observers. The strong anthropic principle claims that the universe must have properties that allow life to develop. The participatory anthropic principle suggests that observation itself might influence the nature of reality. Critics argue that the anthropic principle is unscientific because it's unfalsifiable and doesn't make testable predictions. They also question whether apparent fine-tuning is real, or whether different constants might allow different forms of life. The anthropic principle relates to multiverse theories, which suggest that our universe is one of many with different physical constants. In an infinite multiverse, life-compatible universes would inevitably exist, making our existence unsurprising. 40. The Fermi Paradox. Where is everybody? Given the vast size and age of the universe, the Fermi Paradox asks why we haven't encountered evidence of extraterrestrial intelligence. With billions of stars in our galaxy alone, many with potentially habitable planets, and billions of years for life to evolve, we might expect the galaxy to be teeming with intelligent civilizations. The Drake equation attempts to estimate the number of communicating civilizations in our galaxy by multiplying factors like the rate of star formation, the fraction of stars with planets, and the probability that life develops intelligence. Many plausible values for these factors suggest that intelligent life should be common. Yet we observe a universe that appears empty of obvious signs of intelligence. We haven't detected radio signals from alien civilizations, found evidence of large-scale engineering projects, or encountered visiting spacecraft. This absence is puzzling given our expectations. Proposed solutions to the Fermi Paradox include: life is extremely rare. Intelligence is rare. Civilizations tend to destroy themselves. They're avoiding contact with us. They exist but are undetectable with current technology. Or they're using communication methods we haven't discovered. The paradox has implications for the future of humanity and our place in the universe. If civilizations typically destroy themselves before becoming detectable, this might predict a grim future for humanity. If we're alone, this makes our existence more precious and unique. 41. The hard problem of consciousness. From neurons to feelings, we can explain many aspects of consciousness in terms of brain functions, how we process information, integrate sensory data, and control behavior. But there remains what philosopher David Chalmers calls the hard problem. How do physical processes in the brain give rise to subjective experience? Why is there something it's like to be conscious rather than just unconscious information processing? Even if we map every neuron and understand every connection in the brain, it's unclear why this physical activity should produce the rich inner world of conscious experience. Why should the brain's information processing feel like anything from the inside? The hard problem suggests there's an explanatory gap between objective physical processes and subjective experience. This isn't just about complexity. We can imagine arbitrarily complex unconscious computers that process information without any inner experience. The hard problem asks why consciousness exists at all, not just how it works. It questions whether consciousness can be fully reduced to physical processes. Some philosophers argue that consciousness is an illusion or emergent property that will be explained by future neuroscience. Others contend that consciousness involves non-physical properties that can't be reduced to brain states. Still others suggest that consciousness is a fundamental feature of reality, like mass or charge. The hard problem has implications for artificial intelligence, medicine, and ethics. If consciousness can't be reduced to computation, then digital computers might never be truly conscious. If consciousness involves non-physical properties, this challenges materialist worldviews and raises questions about the nature of reality itself. 42. The binding problem. Creating unity from fragments. Your brain processes different aspects of perception in separate regions: color in one area, motion in another, shape in a third. Yet you experience a unified, coherent perception of the world. How does the brain bind these separate processes into a single conscious experience? This is the binding problem. The challenge goes beyond simply integrating information. Your brain must not only combine different features of the same object, but also segregate features belonging to different objects. When you see a red car and a blue house, your brain must bind red with car and blue with house, not mix them up. The binding problem becomes more mysterious when we consider the timing of neural processes. Different brain regions process information at different speeds, yet consciousness seems unified in time. How does the brain synchronize these different processes to create coherent temporal experience? Various neural mechanisms have been proposed to solve the binding problem, including synchronized neural oscillations, attention-based integration, and convergence zones where different types of information come together. But none fully explains how separate neural processes create unified conscious experience. The binding problem reveals the complexity hidden in what seems simple. The unified nature of consciousness that we take for granted might be one of the brain's most remarkable achievements. Understanding how binding occurs could be crucial for understanding consciousness itself. 43. The free will illusion. Are we the authors of our actions? Every day you make countless decisions: what to wear, what to eat, which route to take to work. You experience these as free choices, but mounting evidence suggests that many of our decisions are made by unconscious brain processes before we become aware of them. Are we truly free agents, or are we sophisticated biological machines following deterministic programs? Neuroscientist Benjamin Libet found that brain activity indicating a decision to move begins several hundred milliseconds before people report being aware of their intention to move. This suggests that consciousness doesn't initiate action, but rather becomes aware of decisions already made by unconscious processes. More recent studies have found that brain activity can predict some decisions several seconds before conscious awareness. fMRI scans can sometimes determine which choice a person will make before they are aware of making any choice at all. This suggests that consciousness might be more like a narrator than a director of behavior. The implications are profound. If our choices are determined by prior brain states, which are determined by earlier states in an unbroken causal chain, then free will might be an illusion. We might be no more responsible for our actions than a computer is for its outputs. But some argue that free will is compatible with determinism. Even if our choices are determined, they're determined by our own beliefs, values, and reasoning processes. Others suggest that quantum indeterminacy in the brain might provide the randomness necessary for free will, though random choices don't seem more free than determined ones. 44. Determinism versus libertarianism. The freedom to choose determinism holds that every event is the inevitable result of prior causes. Applied to human behavior, this suggests that all our actions are the inevitable consequences of previous brain states, which were themselves determined by earlier states, genes, environment, and experience. If determinism is true, then free will is impossible. Libertarian free will requires that our choices are not fully determined by prior causes. We must have genuine alternatives available to us, and our decisions must originate from our agency rather than being the inevitable result of causal chains. For libertarians, moral responsibility requires that we could have acted differently. Hard determinists accept determinism and conclude that free will is an illusion. They argue that moral responsibility is a useful fiction, but not metaphysically real. Soft determinists or compatibilists argue that free will is compatible with determinism. Our actions are free when they flow from our own desires and reasoning, even if those desires are themselves determined. The debate has practical implications for criminal justice, moral responsibility, and how we treat each other. If people's actions are determined by factors beyond their control, should we punish them or instead focus on rehabilitation and prevention? How should knowledge of genetic or environmental influences on behavior affect legal and moral judgments? Recent neuroscience and psychology have provided new evidence relevant to this ancient debate, but they haven't settled it. The question of whether we have free will remains one of the most fundamental puzzles about human nature. 45. Epiphenomenalism. Consciousness as a powerless observer. Epiphenomenalism proposes that consciousness exists but has no causal power. Mental states are caused by brain states. but they don't cause anything themselves. Consciousness is like the steam from a locomotive, produced by the engine, but not contributing to its motion. We experience consciousness, but it doesn't influence our behavior. This view attempts to preserve consciousness as something real while accepting that the physical world operates according to purely physical laws. If consciousness could influence behavior, this would require mental states to violate physical causal closure, the principle that physical events have sufficient physical causes. Epiphenomenalism seems to solve the mind-body problem by making consciousness real, but causally inert. Mental states don't interfere with physical processes, so there's no violation of physical laws. Yet consciousness exists as a genuine feature of reality, not merely an illusion. But epiphenomenalism faces serious objections. If consciousness has no causal power, how can we know about it or talk about it? Our ability to discuss consciousness seems to require that conscious states influence our speech and behavior. The view also makes consciousness seem pointless. Why would evolution create conscious experiences if they do and affect behavior? The debate over epiphenomenalism reveals deeper questions about the relationship between mind and matter, the nature of causation, and the role of consciousness in behavior. It shows how difficult it is to find a consistent position on consciousness that preserves both our scientific understanding and our subjective experience. 46. The Chinese Room. Understanding Without Consciousness philosopher John Searle imagined a thought experiment. A person who speaks no Chinese sits in a room with a comprehensive rule book for manipulating Chinese characters. Chinese speakers outside the room submit questions by passing Chinese text through a slot. The person inside uses the rule book to generate appropriate responses in Chinese, which are passed back out. From the outside, it appears that the room understands Chinese. It provides coherent, intelligent responses to questions. But the person inside understands nothing. They're merely following rules for symbol manipulation without grasping meaning. Searle argues that this shows computer programs, no matter how sophisticated, cannot truly understand language or possess consciousness. The Chinese room argument challenges the computational theory of mind, the idea that consciousness and understanding consist of information processing. If the room can pass any test for understanding Chinese, while actually understanding nothing, then passing tests for intelligence doesn't guarantee real understanding or consciousness. Critics argue that while the person inside doesn't understand Chinese, the room as a whole might understand it. The understanding could be distributed across the entire system, including the rule book and the process of applying rules. Others suggest that sufficiently complex rule following might actually constitute understanding. The Chinese room relates to current debates about artificial intelligence and machine consciousness. As AI systems become more sophisticated, can we ever know whether they truly understand and experience, or whether they're just very good at symbol manipulation? 47. The Turing test paradox. Can machines think? Alan Turing proposed that we judge machine intelligence by whether a computer can convince a human interrogator that it's human through text-based conversation. If a machine can consistently fool humans into thinking it's human, Turing argued, we should consider it intelligent. But this operational definition of intelligence raises paradoxes about the nature of thought and consciousness. The Turing test seems both too easy and too difficult. It might be too easy because a program could pass the test through clever programming and database searches without genuine understanding or consciousness. It might be too difficult because genuine intelligence doesn't require the ability to imitate humans. Intelligent aliens might fail the test. The test also raises questions about what we're actually measuring. Is intelligence about internal understanding or external behavior? Can something be intelligent without being conscious? The Turing test focuses on performance rather than the internal processes that generate that performance. Modern AI systems can perform impressively on many tasks that require intelligence, yet we remain uncertain about whether they truly understand or simply manipulate symbols very effectively. The question, can machines think, might depend on how we define thinking, consciousness, and understanding. The Turing test paradox reveals the difficulty of defining and measuring consciousness and intelligence. It shows that our concepts of mind might be more ambiguous and complex than we initially assume. As AI systems become more sophisticated, these questions become increasingly practical and urgent. 48. The explanatory gap. From brain states to experiences, even if we completely map the brain and understand every neural process involved in consciousness, there seems to be an unbridgeable gap between objective neural activity and subjective experience. This is the explanatory gap, the mystery of how physical processes give rise to the qualitative, subjective aspects of consciousness. We can explain the functional aspects of consciousness, how the brain processes information, controls behavior, and responds to stimuli. But explaining why these processes should feel like anything from the inside remains mysterious. Why should neural firing patterns produce the redness of red or the pain of a headache rather than simply processing information unconsciously? The explanatory gap suggests that there might be fundamental limits to what objective science can tell us about subjective experience. No amount of third-person, objective description seems capable of capturing the first-person, subjective nature of consciousness. This creates a puzzle about the relationship between scientific knowledge and conscious experience. Some argue that the explanatory gap is merely a limitation of our current understanding and will be closed by future neuroscience. Others contend that it reveals fundamental limitations of physical explanation when applied to consciousness. Still others suggest that consciousness involves non-physical properties that can't be reduced to brain states. The explanatory gap has implications for artificial intelligence, neuroscience, and philosophy of mind. If consciousness involves irreducible subjective properties, then creating conscious machines might require more than just replicating brain functions. The gap challenges our understanding of the relationship between mind and matter. 49. The multiple drafts model. Consciousness as competing interpretations. Philosopher Daniel Dennett proposes that consciousness doesn't involve a single, unified stream of experience, but rather multiple parallel processes competing for control of behavior and report. Instead of a central theater, where conscious experiences are presented to an inner observer, consciousness consists of multiple drafts of content competing for influence. According to this model, different brain processes continuously generate interpretations of sensory input, memories, and internal states. These interpretations compete for access to speech, memory storage, and behavioral control. What we call consciousness emerges from this competition, rather than from a single, unified experience. The multiple drafts model challenges our intuitive sense that consciousness is unified and centralized. It suggests that the apparent unity of consciousness is an illusion created by the brain's tendency to create coherent narratives from fragmented processes. We don't have a single conscious experience, but rather multiple competing processes that sometimes align. This model attempts to explain various phenomena that challenge unified theories of consciousness, such as change blindness, split brain studies, and the binding problem. It suggests that consciousness is more fragmented and competitive than our introspective experience suggests. Critics argue that the multiple drafts model doesn't adequately explain the subjective unity of consciousness or the qualitative aspects of experience. The model might explain the functional aspects of consciousness while missing the hard problem of why there is something it's like to be conscious. 50. Integrated information theory. Consciousness as information integration. Integrated information theory, developed by Giulio Tononi, proposes that consciousness corresponds to integrated information in a system. According to IIT, a system is conscious to the degree that it integrates information, meaning that the whole system generates more information than the sum of its parts. IIT provides a mathematical framework for measuring consciousness by calculating the amount of integrated information in a system. Systems with higher phi values are more conscious. The theory predicts that consciousness can exist in non-biological systems, and that some systems we do and typically consider conscious might actually have subjective experiences. The theory makes counterintuitive predictions. It suggests that some simple networks might be more conscious than complex brains, that split-brain patients might have divided consciousness, and that perfect simulations of brains might not be conscious if they do and integrate information in the right way. IIT attempts to solve both the easy and hard problems of consciousness by providing a mathematical theory that explains both functional aspects and subjective experience. It suggests that consciousness is not binary, but exists on a continuum, with different systems having different degrees of consciousness. Critics argue that IIT's predictions match our intuitions about consciousness, and that the theory might imply consciousness in systems where it seems implausible. Others question whether mathematical measures of information integration can capture the qualitative aspects of conscious experience. 51. Gödel's incompleteness theorems. The limits of mathematical truth. Kurt Gödel proved that any mathematical system powerful enough to describe arithmetic must be either incomplete or inconsistent. This means that in any such system, there will always be true statements that cannot be proven within the system. Mathematics, our most rigorous form of knowledge, has inherent limitations. Gödel's first incompleteness theorem shows that for any consistent formal system, there are true statements that cannot be proven within that system. His second theorem shows that no consistent system can prove its own consistency. These results shattered hopes of finding a complete, consistent foundation for all of mathematics. The proofs involve self-reference and diagonal arguments similar to the liar paradox. Gödel constructed statements that essentially say, this statement cannot be proven in this system. If the statement is false, then it can be proven, making the system inconsistent. If it's true, then it cannot be proven, making the system incomplete. Gödel's theorems have profound implications beyond mathematics. They suggest fundamental limits to formal reasoning and mechanical computation. They show that truth is broader than probability, and that some questions might be unanswerable within any formal system. The theorems relate to consciousness, artificial intelligence, and the nature of mathematical knowledge. They suggest that human mathematical intuition might involve non-mechanical processes that can recognize truths that formal systems cannot prove. 52. The Banach-Tarski paradox, doubling a sphere. The Banach-Tarski paradox states that a solid sphere can be decomposed into a finite number of pieces and reassembled into two spheres identical to the original. This seems to violate conservation of volume and our basic intuitions about physical reality. The paradox depends on the axiom of choice in set theory, which allows for the construction of non-measurable sets. The pieces involved in the decomposition are so irregular that they cannot be assigned meaningful volumes. The paradox works by exploiting the infinite complexity possible in mathematical objects. The construction involves rotations and the dense structure of the group of rotations in 3 dimensions. The paradox shows that infinite sets can behave in ways that violate our finite intuitions about space and volume. The Banach-Tarski paradox reveals the difference between mathematical and physical reality. While mathematically valid, the construction cannot be performed physically because real matter has atomic structure and quantum limitations that prevent the required infinite precision. The paradox highlights the role of the axiom of choice in mathematics and the sometimes counterintuitive consequences of infinite sets. It shows that mathematical possibility can diverge dramatically from physical possibility. 53. Gabriel's horn. Infinite surface, finite volume Gabriel's horn is a geometric shape created by rotating the function y equals 1x around the x-axis for x is greater than or equal to 1. This creates a horn-shaped surface that extends infinitely far along the x-axis. Remarkably, this infinite surface encloses a finite volume, but has infinite surface area. The volume of Gabriel's horn can be calculated using integration and equals pi cubic units. However, the surface area integral diverges to infinity. This creates the paradoxical situation where you could fill the horn with pi cubic units of paint, but you couldn't paint its surface, even with infinite paint. This paradox reveals the counterintuitive behavior of infinite objects and the subtle relationships between different geometric properties. It shows that our intuitions about finite objects don't necessarily apply to infinite ones. Gabriel's horn demonstrates important concepts in calculus and mathematical analysis, including improper integrals and the convergence and divergence of infinite series. It illustrates how infinite processes can have finite results and vice versa. The paradox has implications for understanding infinity, geometric measure theory, and the relationship between different types of mathematical measurement. It shows that infinite objects can have properties that seem contradictory from a finite perspective. 54. Hilbert's Hotel. The logic of infinite accommodation. David Hilbert imagined a hotel with infinitely many rooms, all of which are occupied. The paradox becomes more extreme when infinitely many new guests arrive. The manager can accommodate them all by moving each current guest from room N to room 2N, freeing up all the odd-numbered rooms for the new guests. An infinite hotel can always accommodate more guests, no matter how many are already staying. Hilbert's Hotel illustrates the counterintuitive properties of infinite sets. Unlike finite sets, infinite sets can be put in one-to-one correspondence with proper subsets of themselves. This property, called being Dedekind infinite, is actually used as a definition of infinite sets. The hotel paradox reveals that infinity doesn't behave like very large finite numbers. Operations that are impossible with finite quantities become possible with infinite ones. The paradox shows that infinite sets have the same size as some of their proper subsets. Hilbert's Hotel has applications in set theory, number theory, and mathematical analysis. It helps illustrate concepts like countable infinity and the arithmetic of infinite cardinals. The paradox shows why careful mathematical treatment of infinity was necessary to avoid contradictions. 55. Zeno's Paradoxes. The impossibility of motion. Zeno of Elea created several paradoxes that seem to prove motion is impossible. The most famous involves Achilles racing a tortoise. If the tortoise has a head start, then before Achilles can pass it, he must reach where the tortoise was. But by then, the tortoise has moved further ahead. This process repeats infinitely, suggesting Achilles can never catch up. Another paradox states that before reaching any destination, you must first travel half the distance. But before traveling half the distance, you must travel a quarter of the distance. This process continues infinitely, suggesting that you can never begin moving at all. Zeno's paradoxes seem to show that motion requires completing infinitely many tasks in finite time, which appears impossible. They challenge our basic understanding of space, time, and continuous motion. The resolution involves understanding infinite series and limits. While there are infinitely many intervals to traverse, their lengths form a convergent geometric series with a finite sum. Modern calculus provides the mathematical tools to handle infinite processes with finite results. Zeno's paradoxes remain philosophically significant because they reveal deep questions about the nature of space, time, and infinity. They show that mathematical concepts like continuity and infinity can conflict with physical intuitions about motion and change. 56. Cantor's diagonal proof. Different sizes of infinity. Georg Cantor proved that some infinities are larger than others using a beautiful diagonal argument. He showed that the set of real numbers is uncountably infinite, while the set of natural numbers is only countably infinite. This means there are different levels, or sizes, of infinity. Cantor's proof works by showing that any attempt to list all real numbers between 0 and 1 must fail. Given any such list, he constructs a new real number that differs from the first number in the first decimal place, from the second number in the second decimal place, and so on. This new number cannot be on the list, proving the list is incomplete. The diagonal proof reveals that there is no bijection between the natural numbers and the real numbers. The reals form a larger infinity than the naturals. This hierarchy of infinities continues upward without end. There are infinitely many different sizes of infinity. Cantor's work revolutionized mathematics by showing that infinity is not a single concept, but a rich hierarchy of different infinities. It established set theory as a foundation for mathematics and revealed the sophisticated structure of infinite sets. The diagonal argument has applications throughout mathematics and logic, including in Gödel's incompleteness theorems and the halting problem in computer science. It shows the power of self-reference and diagonal reasoning in mathematical proof. 57. The Berry paradox, the number that cannot be named. Consider the smallest positive integer not definable in under 60 letters. This phrase seems to define a specific number, the smallest positive integer that cannot be described in fewer than 60 letters. But the phrase itself is only 57 letters long, creating a contradiction. If the phrase successfully defines a number, then that number is definable in fewer than 60 letters, contradicting its supposed property. But if the phrase doesn't define a number, then we have a meaningful mathematical description that fails to refer to anything. The Berry paradox reveals problems with informal notions of definability and description. It shows that self-reference can create contradictions, even in seemingly straightforward mathematical contexts. The paradox relates to Russell's paradox and other self-referential problems in logic and set theory. It highlights the need for careful formalization of concepts like definability and the dangers of unrestricted self-reference in mathematical reasoning. The Berry paradox has implications for computability theory and the philosophy of mathematics. It raises questions about the relationship between mathematical objects and their descriptions, and the limits of formal definition in mathematics. 58. The Grelling-Nelson paradox. Words that describe themselves. Some words describe themselves. Short is short. English is English. Polysyllabic is polysyllabic. Call these words autological. Other words don't describe themselves. Long is not long. German is not German. Monosyllabic is not monosyllabic. Call these words heterological. Now consider the word heterological itself. If it's heterological, then it doesn't describe itself, which means it's autological. But if it's autological, then it does describe itself, which means it's heterological. We have a contradiction either way. This paradox, discovered by Kurt Grelling and Leonard Nelson, is similar to Russell's paradox, but involves linguistic rather than set theoretic concepts. It shows that self-reference can create contradictions in natural language classifications. The paradox reveals problems with unrestricted predication and the dangers of self-referential definitions. It suggests that natural language might contain inherent logical inconsistencies that formal logic must avoid. The Grelling-Nelson paradox has implications for semantics, logic, and the philosophy of language. It shows that even simple classificatory schemes can lead to contradictions when they involve self-reference. 59. Curry's paradox. If this, then anything. Curry's paradox involves conditional statements that seem to prove anything at all. Consider the statement, if this sentence is true, then Germany borders China. Let's call this sentence C. If C is true, then its conditional claim must hold, so Germany borders China. But Germany doesn't border China, so C must be false. However, if C is false, then the conditional, if C is true, then Germany borders China, is vacuously true, making C true after all. The paradox shows that we can construct statements that seem to prove any conclusion whatsoever. This threatens the consistency of logic itself, since from a contradiction, anything can be proven. Curry's paradox is more dangerous than the liar paradox, because it doesn't simply create a contradiction, it proves false conclusions. It shows that self-referential conditionals can be used to derive arbitrary statements. The paradox has led to restrictions on how conditionals and self-reference can be combined in formal logical systems. It reveals the need for careful attention to the logical structure of self-referential statements. 60. Lt's paradox. Provability and self-reference. Lt's paradox involves statements about their own provability. Consider the statement, "If this sentence is provable, then God exists." Call this sentence LLTB's theorem. Shows that if L is provable, then God exists is also provable, regardless of whether God actually exists. The paradox arises because if L is provable within a system, then the system can prove if L is provable, then God exists. By the rules of logic, this means the system can prove God exists, even if this conclusion is false. Lt's paradox reveals strange connections between provability and truth in formal systems. It shows that statements about their own provability can have unexpected logical consequences that go beyond what we might intuitively expect. The paradox is related to Dell's incompleteness theorems and highlights the complex relationship between provability and truth in mathematical systems. It shows that self-referential statements about provability can lead to surprising conclusions. Lt's theorem has applications in computer science, particularly in the verification of self-modifying programs and recursive systems. It reveals fundamental limitations in how formal systems can reason about their own provability. 61. Schrödinger's cat. Quantum superposition at macroscopic scale. Erwin Schrödinger devised this thought experiment to illustrate the bizarre implications of quantum mechanics when applied to everyday objects. A cat is sealed in a box with a Geiger counter, a radioactive atom, a hammer, and a flask of poison. If the atom decays, the Geiger counter triggers the hammer to break the flask, killing the cat. According to quantum mechanics, before measurement, the atom exists in a superposition of decayed and undecayed states. This means the cat should also be in a superposition of dead and alive states until someone opens the box to observe it. Schrödinger found this absurd, yet it follows logically from quantum theory. The paradox highlights the measurement problem in quantum mechanics. Why do quantum superpositions seem to collapse into definite states when observed? What counts as an observation or measurement? How do microscopic quantum effects translate to macroscopic reality? Various interpretations attempt to resolve the paradox. The Copenhagen interpretation suggests that measurement causes wave function collapse. The many worlds interpretation proposes that all possibilities occur in parallel universes. Objective collapse theories suggest that large objects spontaneously collapse quantum superpositions. Schrödinger's cat remains central to debates about the nature of reality, measurement, and the relationship between quantum and classical physics. It forces us to confront whether the strange world of quantum mechanics applies only to microscopic systems or to all of reality. 62. The double-slit experiment. Reality that depends on observation. When electrons are fired one at a time through two parallel slits toward a screen, they create an interference pattern characteristic of waves. This suggests each electron somehow goes through both slits simultaneously and interferes with itself. But when detectors are placed at the slits to determine which one each electron passes through, the interference pattern disappears. The experiment seems to show that unobserved electrons behave like waves, spreading through both slits and interfering with themselves. But observed electrons behave like particles, passing through only one slit. The very act of observation appears to change the nature of reality. This wave-particle duality challenges our classical understanding of objects having definite properties independent of observation. It suggests that the act of measurement doesn't just reveal pre-existing properties, but actually determines them. The experiment raises profound questions about the role of consciousness and measurement in determining reality. Does observation require a conscious observer, or is any physical interaction sufficient? How does the electron know whether it's being observed? Modern variations of the experiment, including delayed choice and quantum eraser experiments, show even stranger behavior. They suggest that decisions about measurement can retroactively affect the electron's behavior, challenging our understanding of time and causation in quantum mechanics. 63. Quantum tunneling. Passing through impossible barriers. In classical physics, a ball needs sufficient energy to roll over a hill. If it lacks this energy, it cannot reach the other side. But in quantum mechanics, particles can tunnel through energy barriers they classically couldn't surmount. A quantum particle can appear on the other side of a barrier, even when it lacks the energy to go over it. Quantum tunneling occurs because particles are described by wave functions that can extend beyond classical boundaries. Even when most of the wave function is blocked by a barrier, a small portion can extend to the other side, giving the particle a probability of appearing there. This effect is not just theoretical. It's essential for many practical technologies. Nuclear fusion in stars depends on quantum tunneling, as does the operation of many electronic devices like tunnel diodes and scanning tunneling microscopes. Radioactive decay also involves quantum tunneling. The paradox challenges our understanding of energy conservation and classical barriers. How can a particle end up somewhere it shouldn't be able to reach? The resolution requires thinking in terms of probability and wave functions, rather than classical trajectories. Quantum tunneling also raises questions about the nature of time in quantum mechanics. Some calculations suggest that tunneling occurs instantaneously, seemingly violating relativity's prohibition on faster-than-light transmission of information. 64. The EPR paradox. Spooky action at a distance. Einstein, Podolsky, and Rosen devised a thought experiment to show what they saw as an absurd consequence of quantum mechanics. Two particles created together remain entangled. Measuring one instantaneously affects the other, regardless of the distance between them. Einstein called this spooky action at a distance. If you measure the spin of one entangled particle and find it spinning clockwise, you instantly know the other particle is spinning counterclockwise. But quantum mechanics says neither particle had a definite spin until measured. This seems to require instantaneous influence across space. Einstein argued this showed quantum mechanics was incomplete. He believed particles must have hidden variables that predetermined their properties, eliminating the need for instantaneous influences. Local realism, the idea that objects have definite properties independent of observation and cannot instantly influence distant objects, seemed essential to physics. John Bell later proved that no theory of local hidden variables could reproduce all quantum mechanical predictions. Experiments testing Bell's inequalities have consistently supported quantum mechanics, showing that either locality or realism must be false. The EPR paradox reveals the non-local nature of quantum reality. Entangled particles form a single quantum system that cannot be decomposed into independent parts, no matter how far apart they are. This challenges our understanding of space, separability, and the independence of distant objects. 65. The measurement problem. When does the wave function collapse? Quantum mechanics describes particles as existing in superpositions of multiple states until measured. But exactly when and how does this wave function collapse occur? What qualifies as a measurement? And why do superpositions seem to disappear in the macroscopic world? The measurement problem arises because the Schrödinger equation, which governs quantum evolution, is completely deterministic and reversible. It doesn't include any mechanism for wave function collapse. Yet we observe definite outcomes in measurements, not superpositions. Various solutions have been proposed. The Copenhagen interpretation simply accepts that measurement causes collapse without explaining the mechanism. Objective collapse theories propose that large objects spontaneously collapse, quantum superpositions through unknown physical processes. The many worlds interpretation avoids collapse entirely by proposing that all possible measurement outcomes occur in parallel universes. Decoherence theory suggests that interaction with the environment effectively destroys quantum coherence, making superpositions unobservable. The measurement problem remains one of the deepest unsolved questions in physics. It touches on fundamental issues about the nature of reality, the role of consciousness, and the relationship between quantum and classical physics. 66. The many worlds interpretation. Every possibility happens. The many worlds interpretation, proposed by Hugh Everett III, suggests that quantum mechanics describes a constantly branching multiverse, where every possible outcome of every quantum event actually occurs. When you measure a quantum particle's spin, the universe splits into branches, where the particle has each possible spin value. This interpretation takes quantum mechanics literally and completely. There's no wave function collapse. The wave function describes the full quantum multiverse. Every time a quantum measurement occurs, reality branches into parallel worlds representing all possible outcomes. A many worlds interpretation solves several quantum paradoxes. Schrodinger's cat is both alive and dead, just in different branches of the multiverse. The measurement problem disappears because there's no collapse. The EPR paradox is resolved because correlations exist within each branch, but the interpretation creates new puzzles. If all possibilities occur, why do we experience one particular sequence of events? How should we understand probability in a deterministic multiverse where everything happens? Are there infinitely many copies of you making every possible choice? The many worlds interpretation raises profound questions about the nature of existence, consciousness, and personal identity. If every possible version of your life occurs somewhere in the multiverse, what makes your particular experience special or real? 67. The quantum Zeno effect, stopping change. Through observation, the quantum Zeno effect shows that frequent observation can freeze quantum evolution. A quantum system that would normally change over time can be prevented from changing by measuring it repeatedly. Observation doesn't just reveal reality. It can actually stop change from occurring. The effect is named after Zeno's arrow paradox, which argued that motion is impossible because at any instant, a moving arrow is motionless. Similarly, frequent quantum measurements can make change impossible by constantly catching the system in its current state. The quantum Zeno effect occurs because measurement projects a quantum system onto a definite state. If measurements occur frequently enough, the system doesn't have time to evolve between measurements and remains frozen in its initial state. This effect has been experimentally demonstrated and has potential applications in quantum computing and quantum control. It shows that the timing and frequency of measurements can dramatically affect quantum evolution. The quantum Zeno effect reveals the active role of measurement in quantum mechanics. Observation isn't passive, but actively influences the systems being observed. This challenges classical assumptions about the independence of observer and observed system. 68. Wheeler's delayed choice, retroactive reality. John Wheeler proposed an experiment where the decision of whether to measure a photon as a wave or particle is delayed until after the photon has already passed through the experimental apparatus. This seems to suggest that present choices can retroactively determine past reality. In Wheeler's thought experiment, a photon travels from a distant quasar and encounters a massive galaxy that acts as a gravitational lens, splitting the photon's path. Billions of years later, when the photon reaches Earth, astronomers can choose to measure it in ways that reveal either wave or particle behavior. If the photon behaves as a wave, it took both paths around the galaxy simultaneously. If it behaves as a particle, it took only one path. But this decision is made billions of years after the photon supposedly passed the galaxy. How can present choices affect past events? Quantum mechanics suggests that the photon existed in a superposition of taking both paths until the delayed measurement forced it to choose which path it took. The measurement doesn't reveal pre-existing facts, but retroactively determines them. Wheeler's delayed choice experiment has been performed with real photons and confirms quantum mechanical predictions. It suggests that the universe might not have a definite past, independent of present observations, challenging our understanding of time and causation. 69. Quantum suicide. Consciousness in parallel worlds. Quantum suicide is a thought experiment that combines the many worlds interpretation with questions about consciousness and survival. It asks, if consciousness can only exist in worlds where you're alive, what happens when you face quantum events that could kill you? Imagine a quantum Russian roulette device that has a 50% chance of killing you based on quantum measurement outcomes. According to many worlds, both outcomes occur. You die in some branches and survive in others. But if consciousness can only continue in branches where you're alive, you would only experience the survival branches. From your subjective perspective, you would seem to be immortal. The gun would always misfire. The poison would always be a placebo. The accident would always miss you by inches. You would find yourself in increasingly improbable survival scenarios. The thought experiment raises questions about the nature of consciousness and personal identity in a branching multiverse. If there are multiple copies of you in different branches, which one has your consciousness? Can consciousness jump between branches or exist in multiple branches simultaneously? Quantum suicide also relates to anthropic reasoning and the fine-tuning of physical constants. If consciousness can only exist in universes compatible with life, we should expect to find ourselves in life-friendly universes regardless of their objective probability. 70. Wigner's friend. Nested observers in quantum mechanics Eugene Wigner imagined a scenario where his friend performs a quantum measurement in an isolated laboratory. From the friend's perspective inside the lab, the measurement has a definite outcome. But from Wigner's perspective outside the lab, the entire system remains in quantum superposition until Wigner observes it. This creates a paradox about the nature of measurement and consciousness in quantum mechanics. The friend experiences a definite reality with a specific measurement outcome. But according to quantum mechanics, Wigner should describe the entire laboratory as being in superposition until he opens it. The paradox asks whether conscious observers are special in quantum mechanics. Does the friend's consciousness collapse the wave function, or does it take Wigner's observation of the friend to determine reality? Can different observers have different but equally valid descriptions of the same quantum system? Wigner's friend raises questions about the objectivity of quantum mechanical descriptions. If different observers can have different valid descriptions of the same system, what does this mean for the nature of physical reality? Is there an objective quantum state independent of all observers? Recent extensions of the thought experiment suggest that quantum mechanics might need to be modified to handle nested observations consistently. The paradox remains central to debates about consciousness, measurement, and the foundations of quantum mechanics. 71. The strengthened liar. Paradoxes that resist solution, the classical liar paradox, has inspired attempts at solution through various logical frameworks. But strengthened versions resist these solutions by adapting to whatever logical machinery is used against them. Consider, this statement is either false or meaningless. If the statement is true, then it must be either false or meaningless, which contradicts its being true. If it's false, then it's not the case that it's either false or meaningless, which means it must be true and meaningful. If it's meaningless, then it's neither true nor false, which means it is meaningless, seemingly confirming what it says about itself. Strengthened liar paradoxes adapt to whatever escape route is provided. If you declare the original liar statement meaningless, the strengthened version says it's false or meaningless. If you introduce truth-value gaps, new paradoxes arise that account for these gaps. These paradoxes suggest that self-reference in natural language might be fundamentally problematic. They show that our ordinary concepts of truth, meaning, and falsity might be inherently inconsistent when applied to self-referential statements. The strengthened liar reveals the difficulty of providing a complete solution to semantic paradoxes. It suggests that any logical system capable of expressing its own semantic concepts will be vulnerable to paradox, pointing to fundamental limitations in formal approaches to natural language. 72. Semantic paradoxes. Truth that defeats itself. Semantic paradoxes arise when language refers to its own semantic properties, like truth, meaning, and reference. These paradoxes suggest that natural language contains the seeds of its own logical destruction through self-reference and semantic concepts. Consider the truth teller. This statement is true. If it's true, then it's true. If it's false, then it's false. The statement seems to create its own truth value, rather than having one determined by correspondence to reality. This challenges our understanding of what makes statements true or false. The contingent liar creates problems for theories that try to solve the liar paradox by making liar statements contingently false. If this statement is true, then grass is not green. The statement forces any consistent interpretation to make either the statement false or grass not green. Semantic paradoxes reveal tensions between our informal understanding of semantic concepts and attempts to formalize them. They suggest that concepts like truth and meaning might be more complex and problematic than they initially appear. These paradoxes have implications for philosophy, linguistics, and computer science. They show that natural language semantics might be inherently inconsistent, and that artificial languages must be carefully designed to avoid similar problems. 73. Yablow's paradox. Infinite self-reference without circularity. Stephen Yablow discovered a paradox involving an infinite sequence of statements, each saying that all subsequent statements in the sequence are false. Unlike traditional liar paradoxes, Yablow's paradox involves no circular reference. No statement refers to itself, directly or indirectly. Statement 1. For all n greater than 1, statement n is false. Statement 2. For all n greater than 2, statement n is false. Statement 3. For all n greater than 3, statement n is false. And so on, infinitely. Consider any statement k in this sequence. If statement k is true, then all subsequent statements are false. But this means statement k plus 1 is false, which means there exists some statement after k plus 1 that is true, contradicting our assumption. If statement k is false, then there exists some statement after k that is true, but by the same reasoning, no such statement can be true. Yablow's paradox shows that self-reference is unnecessary for semantic paradox. Infinite regress can create similar problems. This suggests that the source of semantic paradoxes might be deeper than previously thought, involving the structure of infinite sequences rather than just circular reference. The paradox has implications for understanding self-reference, infinity, and the foundations of semantics. It shows that attempts to solve semantic paradoxes by eliminating circular reference might miss the deeper structural problems. 74. Cripps paradox. Solutions that create new problems. Picture a brilliant philosopher celebrating what seems like the perfect solution to an ancient puzzle. Saul Cripp had apparently tamed the liar paradox. This statement is false by introducing truth-value gaps. Some statements, he argued, are neither true nor false, but simply undefined, like asking, "What color is Wednesday?" In Cripp's elegant system, the liar statement doesn't create contradiction. It simply fails to receive a truth value. The framework was mathematically rigorous and seemed to dissolve millennia of confusion. But then the revenge paradox is struck back. Consider, this statement is not true. If it's true, then it's not true. If it's false, then it is not true, making it accurate about itself. If it's gapped, then it's still not true, which seems to make the statement correct. Even more deviously, statements emerged like, this statement is either false or neither true nor false. These paradoxes seem to evolve, incorporating whatever logical machinery is used against them. It's like a philosophical arms race, where paradoxes always stay one step ahead of solutions. Crick's work reveals something profound. Perhaps the concept of truth is more elusive than we assume. Every attempt to formalize truth creates new ways for self-reference to slip through our conceptual fingers, suggesting that natural language's flexibility might fundamentally resist complete logical capture. 75. Tarski's undefinability. Truth that cannot be captured. Imagine trying to create a perfect map that shows every detail of the territory with complete accuracy. To be truly complete, your map must include a picture of itself, since the map is part of the territory. But then the picture of the map within the map must also contain a picture of itself, creating an infinite regress. You've discovered something profound. Certain kinds of completeness are logically impossible. Alfred Tarski proved that truth faces a similar impossibility. Any language powerful enough to express its own syntax cannot consistently define its own truth predicate without becoming inconsistent. If a language can say, this statement is true about its own sentences, it can construct liar paradoxes and collapse into contradiction. Tarski's solution created a hierarchy of languages: object language, meta-language, meta-meta-language, and so on. This has startling implications. Natural language appears to contain its own truth concept. We say, that statement is true all the time. According to Tarski, this means natural language must be inconsistent. We cannot have both a complete language and a consistent one. Tarski's theorem reveals fundamental limitations in formal systems and forces a choice between logical consistency and expressive completeness, a trade-off that haunts our understanding of language and truth. 76. The extended Sorites. Vagueness everywhere, the Sorites. Paradox extends far beyond heaps of sand to reveal that vagueness pervades virtually all natural language concepts. Consider, when does a child become an adult? When does a democracy become authoritarian? When does a species become extinct? These questions reveal that most of our important concepts have fuzzy boundaries. The paradox shows that for any vague predicate, we can construct a Sorites series that leads to contradiction. If being 5 feet 11 counts as tall, and if someone 1 millimeter shorter than a tall person is still tall, then eventually someone 4 feet tall must count as tall. Yet this seems absurd. Various approaches attempt to handle vagueness. Epistemicism claims there are sharp boundaries, but we cannot know where they are. Supervaluationism says statements are true if they're true under all reasonable ways of making concepts precise. Fuzzy logic allows degrees of truth between completely true and completely false. But each approach faces challenges. Epistemicism seems to make the location of boundaries arbitrary and unknowable. Supervaluationism struggles with higher-order vagueness. Fuzzy logic faces questions about how to determine precise degrees of truth. The extended Sorites suggests that vagueness might be an irreducible feature of natural language and thought. Rather than being a defect that can be eliminated, vagueness might be essential to how we categorize and understand the world. 77. The preface paradox. Believing contradictions picture a diligent scholar who has spent years researching and writing a comprehensive book on medieval history. She carefully checks every fact, verifies every date, and believes wholeheartedly in each of the 100 historical claims she makes. Yet, being appropriately humble about human fallibility, she writes in her preface, "While I believe everything in this book is accurate, I'm sure it contains some errors. Here is the puzzle that keeps philosophers awake at night. She rationally believes each individual statement in her book is true, yet she also rationally believes that at least one statement is false. This seems to commit her to believing a contradiction, that all statements are true and that at least one statement is false. The preface paradox reveals a fundamental tension in how we think about knowledge and belief. It shows that individually rational beliefs can collectively lead to contradiction. This challenges the principle that rational agents shouldn't believe contradictions, suggesting that perfect logical consistency might be impossible for finite beings dealing with complex information. The paradox extends beyond academic writing to everyday life. You might believe each individual weather forecast while acknowledging that weather forecasts are sometimes wrong. You might trust each piece of testimony from reliable witnesses while knowing that even reliable witnesses sometimes make mistakes. This paradox forces us to reconsider what we mean by rational belief and whether perfect consistency is achievable or even desirable. It suggests that living in an uncertain world might require accepting some level of inconsistency in our belief systems, embracing intellectual humility even while maintaining confidence in our specific judgments. 78. The lottery paradox. When logic meets probability, imagine you're looking at a fair lottery with 1,000,000 tickets, and you know that exactly one ticket will win. For each individual ticket, it's perfectly rational to believe this ticket will lose. After all, the probability is 999,999 in 1,000,000. Following this logic, you should believe that ticket number 1 will lose, ticket number 2 will lose, ticket number 3 will lose, and so on for all 1,000,000 tickets. But here's where reality crashes into logic. You also know with certainty that exactly one ticket must win. So while logic tells you to believe every ticket will lose, mathematical necessity tells you that one ticket will win. You re-forced into believing both, that all tickets will lose and that one ticket will win. A perfect contradiction. This paradox, discovered by philosopher Henry Coburg, reveals the tension between probabilistic reasoning and logical consistency. It shows that applying reasonable standards of belief to probabilistic situations can lead to contradictory belief sets. The paradox suggests that either our standards for rational belief are too low, or perfect consistency is impossible when dealing with probability. The lottery paradox extends far beyond gambling. Consider medical diagnosis. It might be rational to believe that each individual symptom isn't serious, while simultaneously believing that the combination of symptoms indicates something serious. Or in criminal justice, it might be rational to believe each piece of evidence alone doesn't prove guilt, while believing the combination proves guilt beyond reasonable doubt. This paradox forces us to grapple with how we should form beliefs in an uncertain world, where probability and logic sometimes pull in opposite directions. 79. The paradox of analysis. Understanding that teaches nothing. Here's a puzzle that strikes at the heart of human knowledge. If an analysis is correct, how can it be informative? Consider the statement, "A bachelor is an unmarried man." If this analysis is correct, then it's merely restating something we already knew, that bachelors are unmarried men. But if it's informative and teaches us something new, then it seems the analysis must be incorrect, since we're learning something beyond what was contained in the original concept. This creates a dilemma that has puzzled philosophers for centuries. Either an analysis tells us nothing new, or it tells us something new. The paradox suggests that the very enterprise of conceptual analysis might be fundamentally flawed. Think about mathematical proofs. When we prove that the sum of angles in a triangle equals 180 degrees, are we discovering something new about triangles, or just unpacking what was already contained in our definition of triangle? If it's new, how can the proof be valid? If it's not new, why does the proof feel enlightening? The paradox becomes even more puzzling when we consider that some analyses genuinely seem to increase our understanding. Learning that water is H2O feels informative, even though it's supposed to be an analysis of what water really is. This suggests that either our intuitions about analysis are wrong, or there's something more complex happening in the relationship between concepts and their analysis. The paradox forces us to examine the nature of meaning, understanding, and the relationship between language and thought. It reveals deep questions about whether meaning is fixed by definition or discovered through investigation. 80. The paradox of fiction. Caring about things that don't exist, you're watching a movie, and as the hero dangles from a cliff, your heart races with genuine fear for their safety. You know they're fictional. You know it's just an actor with safety equipment on a movie set. Yet you experience real emotions about their imaginary plight. How is this possible? How can we have genuine emotional responses to things we know don't exist? This paradox reveals a fascinating puzzle about the nature of emotion, imagination, and belief. We seem to simultaneously believe that fictional characters do and exist and respond to them as if they do exist. These appear to be contradictory mental states occurring in the same person at the same time. The puzzle deepens when we consider that emotions typically seem to require beliefs. You fear the dog because you believe it might bite you. You feel sad about your friend's misfortune because you believe something bad happened to them. But in fiction, we don't believe the events are real, yet we still feel genuine emotions. Various solutions have been proposed. Perhaps we temporarily suspend our disbelief and really do believe in fictional events while engaging with them. Maybe emotions don't require full belief, but can be triggered by imagination alone. Or perhaps we're responding not to the fictional events themselves, but to the real possibility that such events could occur. The paradox has implications beyond entertainment. It relates to how we learn from literature, why we care about historical figures we've never met, and how we can be moved by hypothetical scenarios in moral philosophy. It reveals the complex relationship between reason and emotion, belief and imagination, reality and possibility. 81. The problem of universals. Do perfect forms exist? Picture the concept of redness. You can point to red roses, red apples, and red fire trucks. But can you point to redness itself? This ancient puzzle asks whether abstract properties like colors, shapes, and numbers exist as real entities beyond the particular things that exemplify them. When we say two roses are both red, are they participating in some universal essence of redness that exists independently of any particular red thing? Plato famously argued that these universals, perfect forms of properties like redness, circularity, and justice, exist in a realm beyond the physical world. Every red thing in our world is merely an imperfect copy of the perfect form of redness. This explains why we can recognize redness in diverse objects and why mathematical truths seem eternal and unchanging. But this view raises puzzling questions. Where exactly is this realm of perfect forms? How do physical objects participate in abstract forms? If the form of redness is itself red, then what makes it red? Another form of redness. This leads to an infinite regress of forms explaining forms. Alternative approaches suggest that universals don't exist independently, but are either mental constructs, useful fictions, or patterns we impose on reality. Nominalists argue that only particular things exist. Redness is just a name we give to certain resemblances between objects. But this struggles to explain why these resemblances seem objective rather than arbitrary. The problem of universals connects to fundamental questions about mathematics, language, and the nature of properties. It asks whether the abstract realm of numbers, sets, and logical truths is as real as the physical world, or whether it's a sophisticated creation of human minds trying to make sense of reality. 82. The mereological paradox. When do parts make a whole? Consider your car sitting in your driveway. It's clearly one object made of many parts: engine, wheels, seats, thousands of components. But here is a puzzle that has stumped philosophers for millennia. At exactly what point do separate parts become a single whole? If you remove one bolt, is it still your car? What about two bolts? Keep removing parts. When does it stop being a car and become merely a collection of parts? This is the mereological paradox, the puzzle of composition. It seems like there should be a precise answer about when parts compose a whole, but any answer seems arbitrary. Why should removing one particular bolt be the moment when a car ceases to exist as a unified object? The paradox suggests several puzzling possibilities. Maybe there are no composite objects at all, only symbols arranged in various patterns. Your car doesn't really exist. There are just particles arranged car-wise. Or perhaps every collection of parts, no matter how scattered, composes an object. This means there's an object composed of your left shoe and the Eiffel Tower. Some philosophers argue that composition is conventional. We decide what counts as a unified object based on our interests and purposes. A mechanic might see a car as a collection of subsystems, while a driver sees it as a single transportation device. But this makes the existence of objects depend on our perspectives, which seems to mislocate the objectivity of the physical world. The mereological paradox reveals deep questions about the relationship between parts and wholes, the nature of objects, and whether the world comes pre-divided into natural units or whether we impose unity through our conceptual schemes. 83. The Grue paradox. What counts as evidence? Imagine a new color word, grue. Something is grue if it's green before the year 2030, but blue afterwards. Every emerald we've ever observed has been grue. By the same logic that leads us to believe all emeralds are green, we should believe all emeralds are grue. But this predicts that emeralds will turn blue in 2030. This paradox, devised by philosopher Nelson Goodman, reveals a fundamental problem with inductive reasoning. We use past observations to predict future behavior, but the Grue paradox shows that the same evidence can support contradictory predictions, depending on how we describe the properties involved. The puzzle is that green and grue are equally supported by our observations, yet they make opposite predictions about unobserved emeralds. This suggests that either inductive reasoning is fundamentally flawed, or there is something special about certain predicates that makes them more suitable for induction than others. Goodman argued that some predicates are entrenched in our language and thought, making them more projectable into the future. Green is entrenched through long use, while grue is a contrived, gerrymandered predicate. But this seems to make the logic of induction depend on arbitrary facts about human language, rather than objective features of the world. The Grue paradox challenges our understanding of scientific reasoning and prediction. It suggests that the logic of evidence might be more complex and convention-dependent than we typically assume. The paradox forces us to examine what makes some patterns of reasoning more legitimate than others. 84. The ontological paradox. Objects with no origin in time travel stories. We sometimes encounter objects or information that exist in causal loops with no ultimate origin. A time traveler receives a book from their future self, travels back in time, and gives the same book to their past self, who later travels forward to give it to themselves. Where did the book originally come from? Who wrote it? It seems to exist without any author or origin point. These ontological paradoxes challenge our understanding of existence and causation. Normally, we expect every object to have an origin, to be created, manufactured, or assembled from pre-existing materials. But objects caught in causal loops seem to exist without any ultimate source. The paradox becomes even stranger when we consider information rather than physical objects. Imagine a time traveler who learns a mathematical theorem from their future self, travels back, and teaches it to their past self. The theorem exists and is true, but it was never discovered or proven by anyone. It simply exists as part of the self-consistent structure of space-time. Some argue that ontological paradoxes prove time travel is impossible. The universe cannot contain objects without origins. Others suggest that causation might be more complex than we assume, allowing for circular chains of causation with no ultimate beginning. The paradox relates to questions about the nature of existence, information, and the relationship between objects and their causal histories. It challenges our assumption that everything must have an ultimate explanation or first cause. 85. Persistence through change. Staying the same while becoming different. You are constantly changing. Your cells replace themselves. Your thoughts evolve. Your body ages. Your personality develops. Yet somehow you remain you through all these changes. This creates a profound puzzle. What makes you the same person over time, despite continuous change? What is the nature of persistence through temporal change? The puzzle applies beyond personal identity to all objects. A river's water constantly flows and changes, yet we call it the same river. A nation's citizens, laws, and territory change over time, yet it remains the same nation. A ship can have all its parts replaced gradually and still be considered the same ship. What accounts for identity through change? Different theories propose different solutions. Substance theories suggest that objects have essential cores that persist through accidental changes. Process theories argue that objects are actually ongoing processes or patterns rather than static entities. Bundle theories propose that objects are just collections of properties, with identity consisting in similarity of property bundles over time. Each approach faces challenges. If identity depends on essential properties, which properties are essential? If objects are processes, what unifies the process over time? If objects are property bundles, why do some changes preserve identity while others destroy it? The problem of persistence reveals deep questions about the nature of time, change, and identity. It asks whether the world is fundamentally made of enduring substances or flowing processes, and whether identity is objective or conventional. 86. Contingency versus necessity. What could have been otherwise? Look around you right now. Everything you see, the chair you're sitting in, the room you're in, your own existence, seems like it could have been different. The chair could have been blue instead of brown. You could have been born in a different country. The universe itself could have had different physical laws. But is this really true? Are there some facts that couldn't have been otherwise? This question divides reality into the contingent and the necessary. Mathematical truths seem necessary. Could 2 plus 2 have equaled 5? Logical truths seem necessary. Could something have been both completely red and completely green simultaneously? But what about physical laws, historical events, or your own existence? The puzzle deepens when we consider the source of necessity. What makes necessary truths necessary? Are they necessary because of the nature of reality, the structure of our minds, or the conventions of language? If mathematical truths are necessary, does this mean numbers exist in some realm beyond the physical world? Possible world semantics attempts to clarify these concepts by saying that necessary truths are true in all possible worlds, while contingent truths are true in some but not all possible worlds. But this raises new questions. What are possible worlds? Are they real or just useful fictions? What determines which worlds are possible? The contingency-necessity distinction has implications for free will, scientific explanation, and the nature of knowledge. If our choices are contingent, this might support free will. If physical laws are necessary, this might explain their universality and predictive power. 87. The possible worlds paradox. The reality of unreality. Philosophers often talk about possible worlds, ways things could have been. There's a possible world where dinosaurs never went extinct, another where you became a professional athlete, and countless others representing every way reality might have been different. But what exactly are these possible worlds? Are they real places, useful fictions, or something in between? David Lewis argued that possible worlds are as real and concrete as our actual world. Every way things could possibly be is a way some world actually is. We think our world is special only because we happen to live in it, just as we think our location is special because we happen to be here. This view, called modal realism, makes possibility and necessity objective features of reality. But modal realism has bizarre consequences. It means that every possible person exists somewhere. There are countless versions of you living different lives in different worlds. It means that every possible story is literally true somewhere. Hitler wins World War II in some worlds, while in others, history unfolds in ways we can barely imagine. The view also raises puzzling questions about knowledge and morality. How can we know anything about other possible worlds if we can't visit them? If all possible actions occur somewhere, does anything we do really matter? Modal realism seems to make ethics meaningless, since every possible choice is actualized somewhere. Critics argue that possible worlds are useful abstractions rather than real places. They help us understand concepts like possibility and necessity without requiring us to believe in the literal existence of infinite alternative realities. But this raises questions about what grounds facts about possibility and necessity. 88. The composition problem. Drawing lines in continuous reality. When does a collection of particles become a genuine object rather than just particles arranged in a pattern? This composition problem asks, under what conditions do parts compose a whole? The question seems simple, but leads to paradoxical conclusions that challenge our understanding of objects and their boundaries. Consider a table. It seems obviously to be one object composed of many parts. But zoom in. Is each molecule of wood a separate object? Each atom? Each subatomic particle? Zoom out. Does the table plus the chair next to it compose a single object? What about the table plus a random rock on Mars? Common sense suggests some collections compose genuine objects while others are mere aggregates. But drawing this line proves surprisingly difficult. Attempts to specify composition conditions face paradoxes. If contact is required for composition, then most objects fall apart since their parts don't actually touch at the atomic level. If shared function is required, then what happens when the function changes or becomes unclear? If similarity is required, then collections of very similar objects scattered across space should compose unified wholes. The problem suggests several radical possibilities. Perhaps there are no composite objects at all, only fundamental particles arranged in various patterns. Your body doesn't exist. There are just particles arranged body-wise. Alternatively, perhaps every collection of objects composes a further object, meaning there's an object composed of your left thumb and Jupiter's third largest moon. The composition problem reveals that our ordinary concept of object might be more problematic than we assume. It forces us to examine whether reality comes pre-divided into natural units, or whether objecthood is imposed by our conceptual schemes. 89. Mental causation. How can minds move matter? You decide to raise your hand, and your hand rises. This seems like the most obvious example of mental causation. Your conscious decision causes physical movement. But this simple action creates a deep puzzle for our understanding of mind and matter. How can something mental cause something physical without violating the principle that the physical world is causally closed? The principle of causal closure states that every physical event has sufficient physical causes. Your hand rises because of muscle contractions, which occur because of neural firings, which occur because of biochemical processes, all following physical laws. If this causal chain is complete, where does your mental decision fit in? How can it make a causal difference without either violating physical laws or being causally irrelevant? This creates the problem of mental causation. Either mental events are identical to physical events, or they're separate from physical events. Dualist theories that make mind and matter separate substances face the interaction problem. Materialist theories that identify mind with matter face the problem of explaining consciousness. Various solutions have been proposed. Some argue that mental events are realized by but not identical to physical events, allowing them to be causally relevant without violating physical laws. Others suggest that causation itself is more complex than we assume, with mental and physical descriptions picking out different aspects of the same causal processes. The problem of mental causation connects to fundamental questions about free will, consciousness, and the nature of persons. It asks whether we're genuine agents or sophisticated physical systems that merely believe they make choices. 90. Trope theory. Properties as particular instances. Traditional metaphysics distinguishes between substances and universals, but trope theory proposes a third category, tropes, which are particular instances of properties. The redness of this apple is a different entity from the redness of that fire truck, even though both are instances of the same type of property. According to trope theory, when two apples are both red, they don't share a universal property of redness. Instead, each apple has its own particular redness trope, and these tropes resemble each other without being identical. Properties become as particular as the objects that have them, eliminating the need for abstract universals. This approach promises to solve several metaphysical puzzles. It explains how properties can be located in space and time, and how objects can have properties without mysterious participation in abstract realms. It also provides a unified ontology where everything that exists is particular rather than universal. But trope theory faces its own challenges. If tropes are particular, what makes similar tropes similar? We can't appeal to shared universals, so resemblance becomes a primitive, unexplained relation. The theory also multiplies entities dramatically. Instead of one universal redness, there are billions of redness tropes. The debate between universals and tropes reveals deep questions about the nature of properties, similarity, and the fundamental structure of reality. It asks whether the world contains repeatable features or whether everything, including properties, is unique and particular. 91. The simulation hypothesis. Are we living in someone else's computer? Philosopher Nick Bostrom proposed a startling possibility. We might be living inside a computer simulation created by some advanced civilization. As our own computing power grows exponentially, we're beginning to create increasingly realistic virtual worlds. If this trend continues, future civilizations might have the power to simulate entire universes, complete with conscious beings who believe they're living in base reality. Bostrom's argument is probabilistic rather than definitive. He suggests that at least one of three propositions must be true. Civilizations rarely reach technological maturity. Technologically mature civilizations rarely run ancestor simulations, or we are almost certainly living in a computer simulation. If advanced civilizations do run many simulations, then simulated beings would vastly outnumber real ones, making it statistically likely that we're simulated. The simulation hypothesis has gained support from unexpected quarters. Tech entrepreneurs like Elon Musk claim the odds we reliving in base reality are billions to one. Some physicists point to features of quantum mechanics and the apparent discrete nature of space and time as potential evidence for computational reality. But the hypothesis raises mind-bending questions. If we're simulated, what does this mean for consciousness, free will, and the meaning of existence? Are our experiences less real if they're computed rather than arising from natural processes? Could we ever prove we're in a simulation, or would the simulation be designed to be undetectable? The simulation hypothesis forces us to confront fundamental questions about the nature of reality, consciousness, and existence. It suggests that the distinction between real and artificial might be less meaningful than we assume, challenging our understanding of what it means for something to be genuine or authentic. 92. Boltzmann brains. When randomness creates consciousness. Ludwig Boltzmann identified a disturbing possibility. In an infinite universe with random quantum fluctuations, conscious observers could spontaneously form without any evolutionary history. These Boltzmann brains would be floating in space with false memories of a past that never occurred, experiencing a momentary illusion of having lived a full life. The paradox arises from thermodynamics and probability theory. If the universe continues long enough, random fluctuations will eventually create any possible arrangement of matter, including configurations that support consciousness. Over infinite time, these random events become not just possible, but inevitable. What's disturbing is that Boltzmann brains should be vastly more common and naturally evolved observers like us. It is much more probable for quantum fluctuations to randomly create a brain with false memories than to create the entire evolutionary history that led to our existence. This suggests that most conscious observers in the universe are Boltzmann brains with completely false beliefs about their past and surroundings. The hypothesis has implications for cosmology and the anthropic principle. If most observers are Boltzmann brains, then our observations of an apparently old universe with consistent physical laws become highly unusual and possibly unreliable. We might need to reconsider our cosmological models or find reasons why Boltzmann brains are less likely than they appear. The Boltzmann brain paradox reveals the strange relationship between consciousness, probability, and cosmic time. It forces us to consider whether our existence is genuinely likely or just a statistical fluke in an infinite universe where anything that can happen eventually will. 93. The problem of infinite regress. Explanations all the way down. Every explanation seems to require another explanation. You ask why the apple fell, and I explain gravity. You ask what causes gravity, and I explain the curvature of spacetime. You ask what causes spacetime curvature, and I explain the stress-energy tensor. But each explanation raises new questions, creating an infinite regress of explanations that seems to lead nowhere. This creates a fundamental problem for human knowledge. If every explanation requires another explanation, how can we ever achieve genuine understanding? Do we need an infinite chain of explanations, or is there some ultimate explanation that explains itself? Both options seem problematic. Infinite regress seems to make explanation impossible, while self-explaining facts seem mysterious. The problem appears in many forms. In logic, every argument needs premises, but what justifies the premises? In causation, every event needs a cause, but what causes the cause? In morality, every value judgment needs justification, but what justifies our fundamental values? The regress problem suggests that human reasoning might be built on foundations that cannot themselves be rationally justified. Different philosophical traditions respond differently to infinite regress. Some embrace it as a feature rather than a bug, arguing that explanation and justification form holistic webs rather than linear chains. Others seek foundational beliefs or experiences that can halt the regress by being self-evident or directly given. The problem of infinite regress points to fundamental limitations in human knowledge and reasoning. It suggests that complete explanation might be impossible, and that all our knowledge ultimately rests on assumptions that cannot be fully justified within our own conceptual frameworks. 94. The ultimate question. Why is there something rather than nothing? This question, which Leibniz called the first question which should rightly be asked, probes the deepest mystery of existence itself. Why does anything exist at all? Why is there a universe, matter, energy, space, time, consciousness, rather than just ... nothing? The question seems to demand an answer. It appears to be unanswerable by its very nature. The puzzle is that any answer to "why is there something?" seems to presuppose the existence of something that could provide the answer. But then we can ask why those things exist, leading to infinite regress or circular reasoning. If we appeal to God, we can ask why God exists. If we appeal to logical necessity, we can ask why logical principles exist. Some philosophers argue the question is meaningless because nothing is not a coherent concept. Nothing isn't a thing, but rather the absence of all things. Asking why there is something rather than nothing might be like asking why there are things rather than non-things. a category error that creates pseudo-problems. Others suggest that existence might be the default state rather than requiring explanation. Perhaps the burden of proof should be on explaining why there would be nothing rather than something. Some quantum theories propose that universes can spontaneously emerge from quantum vacuums, making existence more natural than non-existence. The question touches the limits of human comprehension and language. It asks us to contemplate absolute nothingness and ultimate explanation in ways that might exceed our conceptual capabilities. Yet the question continues to fascinate because it probes the most fundamental mystery of reality itself. 95. The fine-tuning paradox. A universe designed for life? The fundamental constants of physics seem to be precisely calibrated to allow for the existence of life. If the strong nuclear force were slightly different, atoms couldn't form. If the electromagnetic force were altered, chemistry would be impossible. If gravity were stronger or weaker, stars and planets couldn't exist. The probability that all these constants would randomly fall within the narrow ranges necessary for life appears to be virtually zero. This apparent fine-tuning creates a paradox for our understanding of the universe. The constants seem chosen to enable complexity, chemistry, and ultimately consciousness. But chosen by what or whom? The fine-tuning appears to require either incredible luck, some form of intelligent design, or a deeper explanation we haven't yet discovered. The anthropic principle offers one resolution. We observe a life-compatible universe, precisely because we exist to observe it. Universes without the right constants wouldn't have observers to notice their barrenness. From this perspective, the fine-tuning is inevitable rather than surprising. We could unfind ourselves in a universe that could unsupport our existence. Multiverse theories provide another approach. If there are infinitely many universes with different physical constants, then some will inevitably be life-compatible by chance. We find ourselves in one of these rare universes not because of design, but because it is the only type where observers can exist. The fine-tuning paradox reveals deep questions about probability, explanation, and the nature of physical law. It forces us to consider whether the universe's apparent hospitality to life is meaningful coincidence, inevitable selection effect, or evidence of deeper design principles in reality. 96. The multiverse paradox. If everything happens, nothing matters? If multiverse theories are correct, then every possible version of reality exists somewhere. There are infinite universes where you made different choices, where history unfolded differently, where the laws of physics are different. In some universe, you're a billionaire. In others, you never existed. Every possible story is played out somewhere in the infinite ensemble of realities. This creates a paradox about meaning and significance. If every possible choice you could make is actualized somewhere in the multiverse, do your choices matter? If every possible version of your life occurs, what makes your particular experiences special or important? The multiverse seems to democratize existence so completely that nothing becomes unique or significant. The paradox extends to morality and responsibility. If there are versions of you that commit every possible crime and perform every possible good deed, what does moral responsibility mean? If suffering is inevitable somewhere in the multiverse, regardless of what you do, why should you try to reduce it? The infinite multiplication of possibilities seems to dilute the importance of any particular action or outcome. Some argue that the multiverse paradox reveals the importance of perspective and locality. While every possibility might exist somewhere, you only experience one branch of reality. Your choices matter within your particular universe and to the version of people you interact with, even if other versions exist elsewhere. Others suggest the paradox shows that meaning and value are necessarily local and cannot survive infinite replication. Perhaps the multiverse forces us to find significance in immediate experience and relationships rather than in cosmic uniqueness or ultimate purpose. 97. The observer effect. Does consciousness create reality? Quantum mechanics suggests that the act of observation plays a fundamental role in determining reality. Before measurement, quantum systems exist in superpositions of multiple states. Only when observed do they collapse into definite states. This raises a profound question. Does consciousness play a role in creating the reality it observes? Some interpretations of quantum mechanics suggest that consciousness is necessary for wave function collapse. Without conscious observers, the universe would remain in eternal superposition, neither one thing nor another. This view makes consciousness not just a passive observer of reality, but an active participant in its creation. The observer effect extends beyond quantum mechanics to other areas of knowledge. In social sciences, the act of studying human behavior often changes that behavior. In psychology, self-awareness affects mental states. In philosophy, the very attempt to understand consciousness might alter the nature of conscious experience. But the observer effect raises puzzling questions. What exactly counts as an observer? Does it require consciousness? Or would any measuring device suffice? If consciousness creates reality, how did consciousness itself emerge from unconscious matter? How can we study the role of observation objectively when the very act of study involves observation? The paradox suggests that the traditional scientific ideal of objective, observer-independent reality might be fundamentally flawed. Perhaps reality is always relative to observers, always shaped by the act of observation. This would make consciousness not just part of reality, but partially constitutive of it. 98. Last Thursdayism, the illusion of history. Consider this possibility. The universe was created last Thursday with the appearance of age, complete with false memories, fake fossils, and light from distant stars that never actually traveled through space. Every piece of evidence for a past before last Thursday is manufactured, including your memories of yesterday, historical records, and geological formations. This scenario, while seemingly absurd, is logically indistinguishable from a universe with a genuine ancient history. Every piece of evidence for the past could be explained either by actual history or by creation with the appearance of history. If both scenarios make identical predictions about future observations, how could we ever determine which is true? Last Thursdayism reveals the problem of underdetermination in science and knowledge. Any finite set of observations can be explained by multiple theories, including arbitrarily skeptical scenarios. This doesn't just apply to cosmic creation, but to any claim about unobserved events or entities. The scenario also highlights the role of simplicity and plausibility in reasoning. We reject last Thursdayism not because it's impossible, but because it's unnecessarily complex and violates principles like Occam's razor. But this raises questions about whether these principles reveal truth or just reflect human cognitive preferences. Last Thursdayism forces us to confront the limits of empirical knowledge and the assumptions underlying scientific reasoning. It suggests that our confidence in the past might be more faith-based than evidence-based, even when that faith is rationally justified. 99. Eternal return. The universe that repeats forever. Friedrich Nietzsche contemplated a terrifying possibility. What if time is infinite, but matter is finite? With limited arrangements of particles, but unlimited time, every possible configuration would eventually repeat. This means that every moment of your life has occurred infinitely many times before and will occur infinitely many times again, in exactly the same way. The doctrine of eternal return suggests that you have lived this exact life countless times and will live it countless times more. Every choice you make, every word you speak, every thought you think has been repeated infinitely and will be repeated infinitely. The universe becomes a cosmic recording, playing the same song forever. This scenario raises profound questions about meaning, freedom, and identity. If everything repeats exactly, do you have free will? Or are you trapped in an eternal script? If your life has no beginning or end, but cycles forever, what does personal growth or moral progress mean? How should the possibility of eternal repetition affect how you live? Nietzsche proposed eternal return not as a scientific theory, but as a test of life affirmation. Would you be willing to live your life exactly as it is, with all its pain and joy, infinite times? The test asks whether you can embrace existence completely. Including its suffering in this creates a hierarchy of languages: object language, meta-language, meta-meta-language, and so on. Tarski's undefinability theorem has profound implications for our understanding of truth and language. It suggests that natural language, which appears to contain its own truth concept, must be logically inconsistent. We cannot have both a complete language and a consistent one. The theorem relates to Gödel's incompleteness theorems and reveals fundamental limitations in formal systems. It shows that certain concepts cannot be fully captured within the systems that use them, pointing to inherent limitations in self-reference and formal definition. 100. The ultimate paradox. Why something rather than nothing? Standing at the edge of existence itself, we face the most profound question ever asked. Why does anything exist at all? This isn't just wondering about the origin of our universe, but about the very fact that there is something, anything, rather than the pure, absolute nothingness that seems logically prior and simpler. The question appears to demand an answer, yet seems to make answering impossible. Any explanation for existence presupposes the existence of something that could do the explaining: laws, principles, entities, even logical truths. But then we can ask, why do those things exist? We're trapped in infinite regress or circular reasoning. Some philosophers argue the question is meaningless because nothing isn't a coherent concept. Nothing isn't a thing, but the absence of all things. Perhaps asking why there's something rather than nothing is like asking why there are things rather than non-things. A category error, creating pseudo-problems. Others suggest existence might be the default state. Perhaps the burden of proof should be on explaining why there would be nothing. Some quantum theories propose universes can spontaneously emerge from quantum vacuums, making existence more natural than non-existence. Yet the question persists, touching the absolute limits of human comprehension. It asks us to contemplate total nothingness and ultimate explanation in ways that might exceed our conceptual capabilities. This ultimate paradox remains beautiful precisely because it reveals the mystery that there is anything at all to be mysterious about.